Ouais, pour les on va faire. Pour les chiens. On va aller chercher mon casque là-haut. Là, je ferai aller chercher un tout béon. C'est bon. Je vais aller chercher.
Ok.
Ah oui, non, pour m'expliquer aussi le dessin de Ah oui, on va m'expliquer le
ça. Et le micro, non, c'est ça?
Et le micro, que les gens parlent un peu dans le micro.
Plein
dedans, mais pas trop.
Tu as une distance exacte?
Et là, on va
Please. Test. Test. Non.
La dernière fois, c'est la
Non. Good morning, Todd. You're looking for something.
You're the chair? The first chair? Ah, ok, you're
Non. Hola. This morning is Spanish lecture. Hola, ¿qué tal? A mí me gustó la sangría del Montpellier. Madre mía. I was reading it, I was like, sangría de Montpellier. La sangría de Montpellier.
rajouter du poids. Merci. The time.
I have an announcement. I have an announcement. The conference is starting. Quarter to 9. Marlène.
Yeah. Good job.
No.
C'est où pour notre côte? Parce que j'ai pas pouvoir panier.
Ouais,
On est tout bon là, hein. C'est partagé, les micros sont allumés, la caméra.
C'est bon.
Je vais juste chercher mon
We found the scarf, but that's too late. It's mine now. Voilà. Elle est belle, en plus, hein. Je vais faire un cadeau à ma femme, tu vois. Et le cocktail d'hier soir. Ou champagne, gin et puis jus de fruits là, qui donnait de la couleur, ça m'a tué. Ah, c'était le pamplemousse la couleur. On peut pas la faire. Non, c'est 3. Ouais, mais on est 30. Ah non, non, it's great. It's mine. So I have one less announcement to make. I was like very proud of myself. Oh, it's fine! Moi, je l'avais déjà mis, je suis prêt, moi. Bah, elle est bien, mais oui, elle a retrouvé son écharpe. L'écharpe, ils sont
il est dans la poche.
un peu trop prévu. Comme ça.
Ça. Oui, ça c'est normal.
Morning, Chloe.
Let session here, report for duty.
That's you?
That's me. This morning,
It's really you.
I am prepared.
Good one. Okay. We'll have a few announcements, but really nothing very. Aurélien, tu veux faire.
Ouais, sauf qu'il n'y a personne.
Non, mais. On avait dit qu'on faisait les annonces à 9h moins quart.
Ah oui, oui. Ouais.
Bah, juste...
Il faut qu'il y ait 2 personnes qui gèrent la mise à jour de la liste des excursions.
Et les gens qui y vont et qui font.
Ouais, les gens qui sont envoyés.
Hier, les gens.
C'est fait?
Enfin non, c'est
à faire. Ils ont commencé.
Et ça change.
Donc peu de gens.
Ouais, il y en a qui sont arrivés en WeChat, qui arrivés.
Ouais.
Je vais aller voir un peu là s'ils ont remis les.
Ouais, tout c'est fait.
Non, mais on juste en dessous.
Good morning, everyone. Have a seat, please. Now, I see that we've lost a few people. Okay, so a few announcements before we start the day. First announcement, something about the mic here. Ooh. For the presenters, when you are here, that would be great for everybody so that we can hear you from the back and everywhere, to kind of stand here. Not too close to the mic. This is too close. Not too far from the, this is too far. This is the right distance. 18 centimeters, dot 5. Okay? Please. I think you can. No, we don't allow that. Do we? Yeah, well, you can play with the mic if you want. Okay, that was the first announcement. The second announcement, I give the mic to Sarah. Sarah Baudouin.
Instead of going to see each one of you before your talk, I figured it's better to explain it once. So, except for the plenary, you all have 12 minutes for your talk. So, more or less 9 to 10 minutes to speak, and then 2 to 3 minutes for the question. So, there will be someone sitting at the front row showing you the 2-minute signs 2 minutes before the end of your talk. So, at around 8 minutes, so that you know, like, roughly how much left do you have. Thanks.
Thank you, Sarah. We're a bit early, so we have to wait a minute before we actually start. Chloé, do you want to come? Okay, so I'll leave you to it. Enjoy the day and see you around. 18 centimeters.
That's difficult when you're so short.
I think you can.
Oh, yeah.
Yeah.
Perfect. Good morning, everyone. I hope everybody had a great evening yesterday. I'm happy to report that I'm prepared today. And I'm prepared to introduce Mathieu Paquet from the University of Bordeaux. Mathieu has an interest in behavioral ecology and population dynamics, and most of his, or a lot of his work has been occupied with how to make better predictions by accounting for some of the things that we know biologically are very important, but can be kind of tricky to model. And that's like interactions, both within species and between species. So things like social factors, maternal effects, competition, predation, and so on. And Mathieu has written a few papers that I would describe as hold your horses papers, where he and his colleagues basically go, I know you guys have a new toy, but hold your horses now. We need to double check that this actually does what you think it does. And this he did for estimating density dependence and the contributions of immigration, and it's really important contributions to the literature. And I think with that, I will stop talking and hand it over to Mathieu. Take it away.
Thanks a lot, Chloe, for the introduction. So today I'm going to talk about estimating immigration and density dependence using integrated population models. So we heard already yesterday about integrated population models, where you have different data streams within the same population models. And they have a lot of advantages, these models. They can allow you to jointly estimate the demographic parameters and the population size with higher precision than if you would estimate them separately. You can also, because some of the data set shared information, for example, count data has some information about productivity and survival. You can estimate some additional parameters, such as immigration, for which no explicit data is collected. You can estimate the density dependence of the demographic traits while accounting for uncertainty, notably for population size. And we can also estimate how much the variation of the different demographic parameters explain variation in population growth, again within a joint framework. So then I will start, today I will talk about estimating density dependence and its contribution to variation in population growth, as well as immigration. And I will start with the contribution of immigration. So there have been several ways to estimate how much the variation in immigration contributes to the changes in population growth. One is to do a correlation between the number of immigrants you estimate and the population growth rate you estimate. And more recently, there has been a more sophisticated way to do so, which I will talk a bit more about today, which is called transient life table response experiment contributions. So what's important to know about this is that it explains how much the variation in a demographic parameter explains the variation in the population growth rate. And this depends both on how much your parameter vary in time and how much the growth rate of the population is sensitive to this parameter. And one very nice thing about this is that you can then compare the contribution of your different demographic parameters and know how many percentage of the variation they explain. So regarding immigration, it's often found to be, on average, at least the strongest contributor of the variation in population growth in previous studies. So that could mean that the local demography has only a little impact in the population growth of your population, and that most of it is driven by immigration. That could also mean that maybe the management at the local scale is not very useful because everything is driven by extrinsic factors. But one thing we can notice is that often there is very little variation, estimated variation in immigration with very high uncertainty, like in this case, for a northern mid-tier population. And yet we find significant and rather strong contribution of immigration, and on average higher than other parameters. That's a classical result, even though it's, of course, highly uncertain. And I would say that, so yesterday we heard Emmanuel Cam talking about the students not understanding, can we really estimate a parameter for which there is no data and birds are not ringed? And I think it's a nice thought to have, and I think we also all are a bit skeptical and careful when we estimate things we don't see, and so this is a bit intriguing. So it's important to remember that since this is a residual parameter, it can be influenced by a lot of things and a lot of residual noise. For example, the way you parameterize your model can influence how much immigration contributes to the population growth. If you have any temporal patterns you don't account for in your model that influence any demographic traits, it could influence in return the variation you estimate for immigration, and so on. Also, the uncertainty in the estimation of the other demographic parameters. If you use, for example, random time variation, this will tend to shrink your yearly estimate, and maybe this can also leak and influence the variation of immigration you estimate. So we know that immigration is a pool of noise plus true variation of immigration, and it seems important to understand a bit better what proportion of the contribution we estimate is actually due to immigration and not to this unaccounted noise. So what we did is we did some work on case studies I'm not going to talk about today, but you can find them in this paper. And in the same paper, we also did a simulation study where we simulated population with 3 levels of temporal variation in the number of immigrants, different sample size, and different ways to parameterize immigration in the model. So we used IPM with random time variation of the demographic parameters. And for the number of immigrants, we used the 2 most commonly found ways to model it. One is to also use random time variation as for the other parameters. So you have the number of immigrants every year that depends on only 2 parameters, a mean value and a random time variation. Or you have fixed time variation where you estimate the number of immigrants independently every year. So you have as many parameters as the number of years you study. This is much less used. This is the most commonly used way to model it. So what we did is that we simulated what I would call perfect data sets using JAGs, and you can use Nimble as well, where the model you use to generate the data is then the model you will use to fit the data, so that you know that there is no problem of lack of fits and so on. We used a similar model as you can find in the Carey and Shaw book, chapter 11, to model the data. And the number of immigrants is modeled as the number, not a rate in this case. So here, I will not go into the details, but these are the mean values of each demographic parameters, and this means that they vary randomly in time. We used real parameters estimated for a northern wheat year population and sample size we had for this population, which is based on 20 years of data to simulate the different populations. And then for the number of immigrants, we either had a scenario where the number of immigrants was fixed. So there is immigration, but immigration is fixed. And then a moderate variation scenario and a stronger variation scenario that looks like this if you look at the number of immigrants varying in time. And then we repeated the same with a sample size 10 times bigger than the sample size we have for our study population. And we use these 2 ways to model immigration. So this plot shows actually the pooled posteriors and the 95% intervals of these pooled posteriors for the 100 simulations. So what you can see is that when you model no variation in the number of immigrants, you overestimate the contribution of immigration to the variation in population growth. And when you look at the 95% coverage, so that means how often your 95% credible intervals include the true value of the contribution, you can see that these coverages are quite poor. And I would say that here you can notice that the contribution of the number of immigration rate is higher than 0, even with the simulated data. That is because I modeled no variation in the number of immigrants, but here I showed the contribution of immigration rate. So it's not exactly the same thing because immigration rate varies with population size. So you have a small contribution of population size here. But still, we compared these two, and we can see we have an overestimation. Now, when there is moderate variation in the number of immigrants, you can see that then the estimated contribution is good for this parameterization. It's still very high for this one. But another thing you can see is that it's not clearly different from what you would have seen if there were no variation at all. So there is a whole range of variation in immigration for which you cannot really distinguish between the presence of variation or not. So why do we see that? It's not a new problem, actually. The thing is that we estimate temporal variation in the number of immigrants. This value is higher than 0 by definition. And then the more uncertain you are about this value, and the more the mean value of this variation will be away from 0. And so you can see that when you have high uncertainty, it's hard to distinguish the peak of the distribution of your posteriors to distinguish it from 0, unless you have strong variation in immigration, in what case you can start to see a signal. And then if you increase your sample size, if you have a much stronger sample size, it gets much better, but still you always have some overestimation. But here you can start to distinguish from a scenario where you have no immigration. So what can we do? So one thing we can do is to look at the distribution of your posteriors and see if the peak you get seems to deviate clearly from 0 or not. And in that case, for example, you can see it's not so clear. And then you can simulate data based on the parameter estimates you have from your model and fix the number of immigrants through time, like we did for our simulation, and then compare what you estimate without variation in immigration with what you get on your real data. And in our case, we could see that what we estimate on our real data is not different from what we would estimate if there was no variation in immigration at all. Yeah, so here for me, there is no clear evidence that immigration varies and contributes to change in population growth rates. So to conclude on this part about immigration, IPM can strongly overestimate the variation and the demographic contribution of immigration. The bias is less important when you have strong variation in immigration. Of course, it's hard to know if we have strong variation or not in real life. And it gets better with bigger sample size when you have more certainty in your estimates. So such bias can occur, of course, for any additional parameter for which you have no explicit data, and it can occur to a lesser extent to any parameter for which you have little data, little information, as long as you have uncertainty around the estimates of the variation. So that means that it can be hard to compare the contribution of the different parameters for which you have different amount of information. And it can be also hard to compare between different populations for which you have different amount of data. So what we did here and what we suggest is to check for evidence of variation and contribution before drawing conclusion, and you can compare the estimates you get with and without variation in immigration. There are, of course, alternative ways you can use depending on your population and the data you have. You can sometimes, of course, use multi-state models where when you have some type of meta populations, so you can estimate the variation of individuals coming for the total population towards the focal population. This has been done, for example, by Wigman and collaborators for GIS. You can have more spatially explicit models, and sometimes we have information on the location of individuals from a year to the next, and from that you can start to get information about the variation in immigration. So it depends on the data set. Sometimes, especially if your whole population is marked, you can use information about the percentage of unmarked individuals you get in your population, especially if your marking effort is stable. So I know, for example, a paper from Chloe Natter who used information about unmarked individuals to better estimate immigration, and I think it can make sense in some cases. Maybe some data about genetics that could inform us about the likelihood of an individual to be an immigrant or not. And also something that Jonas Knapper did in a paper I'm going to talk about later is that he used like stronger priors to shrink the variation of the demographic parameters towards zero. So in that case, when you don't find evidence for variation in immigration, it doesn't mean there is no variation. It just means you don't have strong evidence for it. So it's not a way to interpret the result you will get, but let's say it's if you want to be conservative, you could use stronger priors on the variation in immigration. And then tomorrow there will be a presentation from Murray, who will talk about also a way to better estimate the contribution of immigration. So I'm looking forward to that talk. And that's it about immigration for today. And then I will talk about how to estimate density dependence in integrated models and their contribution to the variation in population growth. So density dependence is the influence of density or population size on different life history traits, which can in turn influence population size. This leads to population going more or less fast towards a stable population size, or at least an equilibrium around it. And it can be very important to estimate population size, to estimate population trajectory, and to estimate the risk of extension. So there are several advantages of IPMs to study density dependence. One is that you jointly estimate the demographic traits and the population size, and you account for uncertainty and stochasticity in population size. And then you can estimate the density dependence of the traits and derive their strengths on the population growth. But there are still outstanding questions. We still don't really know how accurate are our estimates of density dependence in integrated population models. And there can be potential bias, potentially due to time lags, because the demographic parameters can be influenced by population size, but they influence also population size. So they can be biased due to that, and I will talk a bit more about it. There have been two studies that looked a bit at that. The ones from Abadi et al. Found no evidence for bias in a case where there was density dependence modeled. And then a study from Florian Plar et al. Where they found some bias in some cases. And then a remaining question is, when there is a bias, how does it scale up at the population level? And usually we look at the density dependence on population growth in an ad hoc way, such as looking at correlation between the demographic traits, not between the density at what time and density at the next time step and regressions. And we know that this type of way to do that is prone to bias due to the autoregressive issue that the growth rate estimated as the number of individuals at time t+1 divided by the number of individuals at time t depends on the number of individuals at time t, and you compare it to the number of individuals at time t, so you have the number of individuals at time t in both sides of your equation. Anyway, so what we did is we wanted to know how well IPMs can estimate density dependence on demographic traits. We looked at various scenarios. I can talk more about these ones later with you this week, but today I will talk about various strengths of variation in density dependence and how this can influence the estimates. And then we looked at what are the consequences for density dependence on population growth. And we compared the performance of various measures of density dependence and the consequence of bias for predicting population trajectories. So again, we simulated perfect data set, but then I learned about Nimble, so this time I used Nimble, which is great too. And then that's the way we model density dependence. So we model density dependence on the survival of both young and adult individuals and density dependence on the fecundity. We used 3 levels of density dependence. Either there was no density dependence in any demographic parameters, or a value of -0.1 for the 3 demographic parameters, or -0.3 for the 3 demographic parameters. And then we fitted IPM with density dependence to all the data sets we simulated for 40 years. So what we can see when there is no density dependence is that there is some overestimation of density dependence. So here I show you the 95% interval of the 100 mean estimated values. And in red, you have the true value, which is 0. So yes, you can see there is a small overestimation and the coverages are okay, but here maybe not so okay, but yeah, it's not too bad. And so this could be due to the cross-lag effects that Van der Poel and Bauer talk about in that paper. So then the question is, what is the consequence of that at the population level? Does it have any influence on the strength of density dependence we estimate on the population growth rate? If you do correlations or regression, what you see is that we then have a strong overestimation of the density dependence. And in that case, the coverage gets very bad. This can be due to 2 things. The first one is it can be due to this bias I showed you just before in the different demographic parameters that scale up at the population level, but also it can be due to this autocorrelative problem I talked about, where you have the population growth rate that depends on the number of individuals at time t, but then you get the number of individuals at time t in both sides of your equation. So there is a very nice paper from Le Breton in 2009 about this problem, and earlier paper from Saint-Amand about it as well. So it's an old problem. But is there any solution? So what we did, then we tried a way suggested by Landy to estimate density dependence, which is a rate of return towards equilibrium. So in that case, you don't have the autoregressive problem. And what you can see is that you still get an overestimation, but this time the coverage is still not good, but it's far better than what you get for correlations or regressions. And then we used again this LTRE contribution, but Jonas suggested a way to partition the contribution of the demographic parameters one step further. So what he suggested is to look at the contribution of the covariates of your demographic parameters. So how much density dependence or temperature or rainfall influence the changes in population growth rate. And this paper is there is a preprint on EcoEvo archive if you want to look at how to do that. So we looked at the contribution of density dependence of all parameters to the changes in population growth, and we get exactly similar results. So in that case, this means that 14% of the variation in population growth rate is explained by density dependence. That's what we estimate, although we know that the true value is 0. So these are better than these, but still not, we still get a bias. Okay. So does it have an impact on the predictions? So then we fitted our models to without density dependence, our model with density dependence, sorry, to simulated data without density dependence, and then we project the predictions for 40 more years, and we can compare it with the true simulated value. And I give some example of the 100 simulated scenario populations, and you can see that sometimes you get a strong overconfidence in your population size in these cases. And here is the coverage of population size. So it means that we get too confident as we get away from the, as we predict in time. One thing you can see is that when you have strong variation in population size, you are better at estimating the fact that there is no density dependence. Whereas when you have little fluctuation, then it's harder for the model to capture the fact that there is no density dependence going on. So that means also that extinction probabilities are likely underestimated because of this bias. And then we did a perturbation study where we simulate a drop in population size, and we see what we estimate as the return rate of the population to the stable equilibrium in scenarios where there is no density dependence. So this is a way to visualize a bit this rate of return towards equilibrium. And you can see that we estimate some rate of return, more or less strong, depending on the populations. And that leads to an overestimation on average of population size. So in such case, in such scenarios, you will, even more underestimate the likelihood of extinction. Then with varying levels of density dependence, we still get a bias in the estimation on the different demographic parameters and on the contribution of density dependence to change in population growth rate. But at least the coverages get better. And I won't show the results here, but this has much slower consequences for the predictions of population trajectories and sizes. To conclude about density dependence, IPMs can strongly overestimate the intraspecies density dependence, particularly on population growth rate. We looked at 2 ways to do that. That seems better than regression and correlations, but still they are prone to bias when there is low variation, when there is low density dependence. And again, I would suggest as a way to check for evidence of density dependence to use simulation and run IPMs with your predicted estimates without density dependence to see how far this is from what you estimate with your true data sets. So I have little time left to talk about what I'm doing at the moment with Frédéric. So we work on identifiability of multi-species IPM with species interactions. So far, there's been only few IPMs with interspecific interactions I know of. And so they look at interaction between two species, either competition interactions or predation interactions. And we were interested in knowing how well we can estimate this interspecific density dependence. So one question is that, yeah, can we use two species IPM to estimate species coexistence, for example, via some invasion criteria you can calculate? For example, there is some parametrization for which you can estimate invasion criteria that can help you estimate species coexistence, and we could use IPMs to estimate that. What we did so far is that we built on a previous study from Barracan and Jimenez where they simulated a predator-prey model, and we fixed the interspecies interaction to 0 to see if we have a bias in such cases. And we also look at whether this bias is influenced by the presence of random time variation in the vital rates or not. This is a variable in EcoEvo archive and has been submitted to PCI ecology. Briefly, what we found when we fixed the interspecies density dependence to 0 is that on average, we don't see evidence for bias in such cases. So that's good news. So here, it is the predicted annual value of the different demographic parameters, depending on the variation in abundance they depend on. And you can see that on average, they are around 0 and the coverage of the parameters are good. And we started to look at competition structured populations. So this is some work that is ongoing. I'm not going to talk about it today during this presentation. I'm happy to talk about it later. But some thoughts about it that are important to consider is that if you have a bias in interspecies interactions, that could mean that species with different sample size could be estimated as with different competitive levels, and it would be nice to avoid such cases. And then if you have cases where interspecies interactions are not biased, like we found for the predation model, but intraspecies interactions are biased, you could then have a bias in the estimation of species coexistence. So to conclude, I'm not a statistician, so I found simulations to be a great tool to compare what I find with my real data with what I could find with simulated data. I know how it is made, and the new tools such as JAGs and Nibbles are really great to do that. If you are able to fit a model with JAGs and Nibbles, you are able to simulate data with JAGs and Nibbles. So. And IPMs, to me, they look increasingly complex and all different, and it feels hard to get some general formulas about how to estimate bias. For simple models, there have been ways, but that's why relying on simulations, it can be useful in such cases. And I will stop here. I want to thank you and thank the organizer and everybody who helped somehow, one way or another, with this work. Thank you.
All right, thanks a lot, Mathieu, for a very clear and nicely presented talk. Do we have any questions anywhere? I'm sure we do.
Hi, Mathieu. Thanks very much for the very nice talk. I had a question related to the first part of your talk. For me, one striking assumption of IPMs is that immigrants have the same demographic contribution to the population as locals. They have the same survival and reproduction rates. And I was wondering if you had made any simulation to see the impact of this and if you had any thoughts on that.
I haven't. My guess is that it will have an effect. I mean, if in reality they have different demographic parameters, it's likely to influence the outcome. But I'm not sure. I haven't looked at it. I don't want to. But it's a good point. That's an assumption we made. Yes.
Any other questions? Doesn't look like there's anything on the Zoom. Yes.
I'll ask this question because I'm going to have to revise my talk for Friday based on your talk, but does it make any difference if you estimate density dependence within the IPM versus estimated with posteriors?
It's in some cases, no. So what we have done is that we have also run IPM with just random variation, and a posteriori we look at the correlation between population size and growth rate. We find the same bias. It's not stronger or less strong than so in this case it doesn't seem to matter, which can make things much faster. But I wouldn't be sure in all cases this is true.
All right, thanks a lot for questions. And,
There's the last question, but
I think we're out of time. But grab Mathieu as he goes out to get coffee. Thanks a lot, everyone.
Hi, everyone.
Okay, so our next speaker is Janelle Badger, and she'll be talking about integrating movement data into market recapture analysis, case study of the false killer whale in the main Hawaiian island.
I'm grateful to be here to chat today about our method to estimate abundance of false killer whales in Hawaii by accounting for space use. This is a collaboration between myself and a whole cast of co-authors here. And since I don't have a ton of time, I'm just going to jump right in. The insular population of false killer whales in the main Hawaiian Islands is small and highly mobile, making them sparse throughout their range. They preferentially associate as for social groups or social clusters, and unfortunately were listed as endangered under the ESA in 2012. But the stock is the most thoroughly studied population of false killer whales in the world, with data streams including photo ID dataset of distinctive individuals collected by many contributors and curated by the Cascadia Research Collective, and also movement data from tagged individuals. And however, due to some necessary sampling constraints as well as false killer whale behavior, abundance estimation is really challenging. So surveys are designed to maximize encounter rates. So there's this variable effort among island areas, and these surveys are almost exclusively conducted on the leeward sides of islands protected from the trade winds. Surveys are also only able to encompass a small portion of the populations, or in fact any given individual's range on any trip. So without further information, we don't know animal availability to the survey efforts, and using conventional market capture models, the issue is interpreting what portion of the population any resulting abundance estimate actually refers to. So making any sort of trend detection really difficult, which is troubling for an endangered species. And if we think about, trying to tackle this question, if we think about availability as the overlap of animal presence in our sampling effort, well, we generally know where has been surveyed or where we've put in effort from most of the contributors, and animal presence and space use may be estimated using things like available satellite telemetry data. So we wanted to improve the abundance estimates by incorporating animal availability into our framework, and we did this by developing what I'm calling just like a pseudo-spatial capture model, which is just really a practical way to account for space and spatial temporal variation and animal availability within a capture model that doesn't actually require you to build a spatially explicit model. So first we summarize the yearly survey effort, then model animal space use from telemetry data, determine the overlap between these processes, and use that overlap as covariate for detection. Okay, so for the remainder of the talk, I'll go into a little bit more detail on how we kind of use this method in the abundance estimation for the main Hawaiian Island false killer whales, and assess the model performance, and then show you guys some of the results. So we summarize the yearly survey effort using simple kernel density estimates from the effort data from each year, using a bandwidth chosen based on the average sighting distance from research vessels of about 1.5 kilometers. So on the right here, you can see the effort in 2011 on the top, on the bottom, the resulting effort kernel. And then to define animal space use, we just simply fit the telemetry locations to a continuous time movement model to account for location error, describe the imputed tracks from that model using a kind of pseudo-autocorrelated kernel density estimator to create these kind of heat maps of individual space use. So then I treated these movement tracks were tagged animals as a sample of population space use. Here, the fact that they roam about in clusters work to our advantage. So if two individuals are of the same cluster, their movements are very likely correlated. So we create cluster or social group level utilization distributions by averaging the tagged individual kernels by cluster. So here are the 4 resulting social cluster utilization distributions for this population. And then, so for each distinctive individual in our photo ID capture data set, their space use is assigned as their social cluster UD. So we just find the overlap of these two processes. So right here, you can see the normalized cluster 1 space use kernel or UD on top, and the effort kernel in 2011 on the bottom, and they overlap okay, which is reflected in the standardized overlap of 0.22. Okay, so for this analysis, we use this method in a multi-state formulation of the Jolly Zebra population model in a Bayesian framework with detection probability P varying by time as a function of that overlap described by this parameter delta. And then to assess trend, we just embedded a regression on the abundance estimates at each iteration of the MCMC such that so that the uncertainty in our population size estimates is appropriately propagated to trend. And then we evaluated the model fit using an approximate leave-without cross-validation technique, LUIC. So in order to see if this was actually going to be useful, we decided to just simulate some data with known parameters and looked at how well this model of incorporating this overlap versus a more conventional Jolly Zebra model could, how they relatively perform. So we first, we submitted tracks of the animals, this correlated random walks with more directed movement. And you can see an example individual from each of the 3 groups on the map here in blue. Then for each year, we also surveyed tracks of survey efforts right at 3 points across the map as correlated random walks with higher area restricted search. An example year is on this plot in orange. And these surveys would detect the moving individuals that they came within 1 kilometer of the survey tracks, populating an encounter history for these fake animals. Consider 2 complications here, so detectability and temporal variation in cluster movements, such that a static utilization distribution for animal space use would not characterize the cluster movements very well. So for each set of these conditions, we simulated 50 data sets, went through the whole process, and ran the model with and without the overlap. And let's see how that went. So I focused on low encounter rates or detectability, as that seems most relevant to our system. So space use is well characterized by static animal UD, or if there's constant space use, there's a 14% increase in accuracy and abundance estimates, 12% increase in true trend detection, and an almost 2-fold increase in posterior precision of abundance estimate. And then when space use is not super well characterized, so when space use is variable, but we assume that static UD, we still see a slight improvement in the pseudospatial model, as it is still explaining some variation in cluster space use or effort. So at the very least, if we aren't characterizing species well in using this method, it doesn't reduce the quality of these estimates fit by the pseudospatial model below that of the conventional model. So now that we've done our best to kind of assess model performance, we'll dig into the updated abundance estimates for this population. So the data that we'll be using for this is encounter histories from 202 individuals from 1999 to 2021, and then 52 tags deployed on members of this population from 2007 to 2022 to calculate those cluster UDs. Importantly, in using photo ID data capture and capture analyses, we only directly estimate the number of distinctive individuals, and we must adjust these estimates by proportion distinctive, which is theta here. We estimated a time-specific proportion distinctive using a generalized additive model on the number of distinctive and non-distinctive individuals photographed at all these encounters. We extracted parameters from the GAM fit to provide a multivariate normal prior for the series of proportion distinctives over time, summarized here on the left. So the black line and the gray shading is the GAM model fit and confidence, whereas the red lines are draws from the multivariate normal prior. So by embedding this within the MCMC, we account for that variation due to uncertainty in the proportion distinctive within the total abundance estimates. All right, so finally, here are the abundance estimates. To be clear, these are not final, they're pending review, so please do not cite. This figure just shows the point estimates and 95% credible intervals for each year. The posterior distribution for the slope parameter and the regression of the total abundance over time, which is our method of trend estimation, is shown here. Dashed line is posterior mean, and it has a 95% credible interval that spans 0, but it's heavily trending negative. However, this n over time is maybe not linear, and so linear regression to determine trend is perhaps an appropriate trend for also just the last 10 years, where the relationship is roughly linear, and the 95% credible interval for trend over that period is distinctly negative. So in conclusion, we developed and applied an abundance estimation framework that informs availability of animals to sampling using auxiliary telemetry data to help alleviate sampling bias. Simulations confirm that this method provides more precise, accurate estimates of abundance and trend, even when animal space use is poorly defined. And then using this method, we found a decline in abundance of this population for at least the last 10 years, which is an especially concerning outcome for this endangered population. Okay, so with that, I'll take a second to thank all my collaborators and contributors, and I'll happily take some questions now. But if you have any other thoughts or suggestions you don't want to share here, please feel free to email me.
He's not online. Okay, move on. Janelle's not online, so we're going to move on to the next talk.
Okay, so our third speaker of the session is Sarah Gomez, who's going to be talking about linking variation in juvenile meerkat foraging behavior to growth rates and survival there.
Good morning, everyone. So the work I'm going to present is part of my master project that I'm actually currently doing with Montpellier, Swansea, and Cambridge University. And it is about meerkat foraging behavior and the link with growth and survival. And it is a biologging and state space modeling approach. So just to introduce quickly, I'm going to talk a lot about behavioral ecology and especially foraging behavior, which is a special interest in this field because all animal needs energy to live. And I'm especially going to talk about meerkats because it's very important for them to forage, and it's special for them because they are learning how to forage when they are young. And then when they reach 3 months old, they just become independent and they just have to forage by themselves. And this stage of life is critical in their life and can carry over to survival or reproduction success later in life. So this is where behavior is linked to population studies and demographic study, and understanding the relationship between foraging behavior and growth and survival is a very complex goal, but this is what we are trying to do in my master project. So what did we do? So we have a lot of amazing data from the Kalahari Meerkat project. We have biologging data for 46 juveniles during the transition stage to independence. We also have video recordings of 10 of these juveniles. And we have a lot of weight data recorded during the whole life. And with this data, we use biolinking and video to classify the behaviors and in order to have the complete time budget to spend in each behaviors. And we use these behaviors with the weight data to model and create a Bayesian state space model. And this model will give us a lot of information. We will reconstruct the curve of weight, the complete curve. We will be able to estimate the cost of each behaviors and estimate foraging efficiency and foraging learning rates. So I will be quickly explaining how we classify the behavior. So we have accelerometer data. So around the meerkat, we have 3 axes that vary according to the posture and the activity of the meerkats. And so as you can see in here somewhere, depending of the behavior, we would see several different patterns on the 3 axes, and we can then classify the behaviors according to these values here, and we can classify the foraging behavior, and we will know how many times they spend in each behaviors. And for example, here, this meerkat is spending 26% of his time foraging. And so we use this time budget into the state space model. So quickly, the state space model is a quite easy model compared to all these presented. And it's basically a time theory where we look at the mass at time t+1, which is based on the mass at the previous time, plus the weight they gain between these 2 times. So it's basically the input less expenditure of their activity. So if we go into details, the input is the time they spend foraging. So I know that from the classification. Time RI, which is foraging efficiency. So this is how good they are to forage when they spend 1 hour foraging, how good they are. And this parameter is very important in terms of ecology. We will add a lot of things into the model. We will add random effect on this RI, several variables into the model. And we will also allow this RI to vary over time. At each time t, we will have several different values of RI. So this was for the input, and then we have the expenditure. Here it's basically the same. It's the time they spend in all the other behaviors times the energy cost of all these behaviors. And that's all, more or less. And we tried several options into this RI, and when comparing the model, we realized that the more complex model was more or less selected. So we were quite happy and we were excited because it means that something is happening with this foraging efficiency. And I will show you the first result we had. So first thing that it does is reconstruct the complete weight curve of meerkat. So we have weight of meerkat recorded on the field, but it's not complete weight. And then the model reconstructs the curve like this. So here we have 1 weight per hours. And you can see that the curves increase and decrease according to the time they spend in each behaviors. So for example, if we zoom, we can see that this is daily variation. We can see that during the night, they lose weight, and during the day, they gain weight because they are looking for food during the day. So this is the first thing the model does. Then the second thing is estimating the cost of each behavior. So here you have posterior distribution of this estimation for foraging, running, and other behaviors. Then it estimates foraging efficiency, so RI. And here, as we had a random effect, we have 1 foraging efficiency per individual. So we have 1 posterior distribution per individual. Here, you can see that these individuals are less efficient than those 1. And in the end, we just have an index per individual that we could use in further model, like looking, okay, this one is good, so what does it mean? What's the consequence of that? And so forth. We also have 1 estimate per family. We know that this family is less efficient forager than that one, and it's important because they are social mammals. Also, I'm going to show a lot of things in this RI, but also in this RI, it includes several variables, as I said. And so we can estimate the impact of this variable on the RI. So if I go quickly, because I know I don't have time, it means that we have 3 variables. So the bigger they are at independence, so just before independence, the more efficient they will be, the bigger RIs they will have. On the other side, the bigger they are at emergence weights, so at emergence, so when they just go out of the burrow, the less efficient they will be. And interesting thing is that rainfall has no real effect. Whatever the rainfall that they add during the beginning of their life, they won't have different RI. So, okay, but we could add other variable, is just the first one we tried. And the last thing included in this RI is that we allow this RI to vary over time. So here we can see that during the 2 weeks of the coloring period, the value of RI is increasing. So they are still learning how to forage. They become more and more efficient. And one work we want to do now, and that is still running right now, is that we want to have different curves between the different slope between individuals to see if some individuals are just learning more than others at this time of their life. And yeah, this is what we can include in the model, and we're still adding things into this RI, foraging efficiency. So just to conclude quickly, what we did is that we created a way to classify behaviors, which is different from the machine learning because it's not a black box. You can change the value of your classification according to the biomechanic of the meerkat. And we can use this in further studies, and we're still improving this because we added another behavior now, which is digging. We created a model that gave us a lot of things, and a lot of things that we could then look at the consequence of these values. So we have different foraging efficiency, and what we want to do now is looking at the consequence on growth and survival. So as you can see here, I started doing this. I already have some results, but it's not ready, I think. And yeah, so we are trying to do that. We also want to include this foraging efficiency into a population model like IPMs. And this is what I'm currently doing for my master. So I still have 4 months. So if you have any suggestions about that, I'm very happy. Even if I have a great team, I'm still happy to contributions. So thanks for your attention.
Time for questions.
Hi, Sarah. Thank you for your talk. It's very impressive work at the master level, and very interesting too. I was wondering if the juveniles for which you have the accelerometer data, they belong to the same breeding groups, and if you have information on the size of the groups and how it could influence their foraging efficiency and all the parameters you look at.
Yeah, they come from different groups. We have 9 families that are in the same park, but at different places. And we do have all information about everything in this project. So I can have information about vegetation or this kind of thing that we would like to include in the model, because we think that efficiency will depend on like the landscape of the group. So yeah, definitely. But we have all information. That's a good point.
Time for one more.
Thanks a lot. It was very interesting. I think you mentioned that for estimating the energy of each behavior, you had to use priors.
Priors, yes.
And how did you choose these priors?
It was based mostly on the literature and on people in the field. So we looked at the total energy needed for meerkats when they are babies, when they are adults. And also we looked, it was a long time ago now, but we looked at the gain of a scorpion, for example, how many scorpions I would need. We use literature for different papers, like from zoological papers. And yeah, we put priors.
Great, thank you, Sarah.
Thank you.
Our next speaker is Guillaume Souchet, who's going to be talking about following the yellowbird road.
Yeah. Okay. So, good morning, everyone. I'll be talking, it won't be lots of methodological stuff and result stuff. It's just a project we launched last year. and yeah, follow the yellow brick road. It was also a good excuse to be here this year. It will be talking about farmland, the evolution of this landscape and biodiversity. So this is somewhat common since World War II. There was agricultural intensification. So in terms of land use, practice, and mechanization, and everything since the last 50 years has changed the landscape. Here is just aerial photograph of the study area. So you can see that a long time ago there was lots of really small plot and edges and everything, and now just not really the same. So some homogenization and simplification of the habitat. And so for several farmland species, it just means that some degradation and loss of habitat. And so this is the general background. And about predation, this landscape is a key component for predation interaction because all croplands are just useful for every species. It can be either food for food resources or for shelter. And for predators also, edges are very useful. It can be used as perch or just a way to move into the landscape. So any change on the landscape can have an impact on communities dynamic and also on species dynamics. We try to investigate into a vertebrate network, also because there was several difference in abundance evolution of the species. For instance, we have some data suggesting that there is an increase in generalist predators such as red foxes or common buzzards. And on the other way, there is a decrease of several prey species, especially in mammal and birds. So for rabbits, partridge, skylarks, so not on the good way. So we wanted to study the impact of farmland evolution on the impact of on the trophic relationship. So we use the Ukraine hare as a study species because it's an alternative, especially the leveret, to rodents. You can find it everywhere in France and in every type of farmland. And also we found that there was a big decrease in breeding success of this species. So since about 30 years, when we're looking at the breeding success in hunting bag, we found that during the 90s, it was a ratio about 2 young per adult, and now we are just 1 young per adult. We think that it's likely related to survival. We have no clue about a decrease in fecundity data, so it could be related to survival. So at this time, we say, okay, let's study leveret survival. But, because there is always a but, because this is a critical stage, this is also a very cryptid individual, and it's quite difficult to find them. And as we saw yesterday, sometimes when you have some individual, you are not sure about are they representative or not of all the individual. So sometimes you can find some leveret on the trail, or sometimes just inside crop, but we were not sure if we just want to study this individual as a representative or not of all individual, especially when you want to study survival and your data set is quite small. So the idea was just to try to catch those and to follow them to find the leveret. So we started last year. So in Brittany, in western part of France, we have a study area about 20 kilometers squares, and we equipped last year 10 female with GPS collar. What we got to be able to find the leveret, you have to know that suckling is only once per day. It's only about 2 or 3 minutes per leveret every day, and it's about 1 hour after sunset. So we try to get the localization just at this particular moment. And we follow 9 female, one just escape or die or we don't know what happened. And we get that kind of data. So we have some departure of the dose. And for every day, we have a trajectory toward sometime toward the same, some convergence to a spot. And when there was something like that, we just tried to go by night with thermal binocular and to see if there was something or not. So doing that, we found 6 little places, and yeah, with this cute little boy or girl, I don't know. So sometimes we found only 1, sometimes 2, sometimes 3. And for this one, it was just, we didn't find them on the ground, we just observed them with binoculars. But after that, when we were going to into the plot to see what they were, there was just nothing left, because they're quite quick. And to find the leverage is nice, but after that, because we can't go on the field every time because it's quite far from where we are working, and also because sometimes you can go to the field and there is about wheat about this high, or it's in maize or everything else, you can't really observe the circling or the leverage. So we wanted to have some method to get the information. And so look at some package, and there is the NestR package, which analyze recursive movement. So you can find a spot using your data. This is a package developed by Simona Picardi and some other people. And for instance, for this dose, whose departure was here and always going here, and we found 2 leverages here. We just enter the data into the package. You can try to find good parameterization, and you can start the breeding season. How long is the breeding season? Yeah, just for the information, it was at the beginning developed for birds, so it's all about nest. But yeah, birds, mammals, everything. And when you put it into the package, it can, when you give some information, how many days, how many consecutive days you can, the female is supposed to go, you can find some places. For instance, here is the spot where we found the leverage, and here is the spot where the package said, okay, maybe there is something here. Yeah, there is the same here for another female. And for this one, we had data from February to July, and due to trajectories, there is potentially 4 different places. Yeah, maybe I should have said that the breeding season starts in January and ends in October. And a female can have from 0 to 7 liters. So you can find many of them everywhere. Okay. And yeah, based on the localization and the moment during the year of this, we also try to investigate some characterization of the territories, because as we can't go every time on the field, it could be a good thing to have some algorithm after that to find it quite automatically. And we just, for the moment, found not so many things, but at least, yeah, this is for the 9 nodes. There is just a quick difference between trajectories during the circling moment and outside. And there is apparently a longer distance between our localization every 2 minutes. Nope. Yeah. So every time there is a longer distance between every segment than when it's not during the second time. So what we're going to do next is that this year we equipped 15 new female. We want to do that also next year to be able to have more little places, more data to implement to feed the algorithm. And after that, we like to investigate why we can find them at this place. Is it because of the height of vegetation? Is it because this is wheat, or this is maize, or this is pasture? We don't know yet. So is there habitat selection or not? And after that, we want to go to the next step. So assessing potential risk of mortality. Are there some places more prone to predation? Is it predation by mammals or avian predation? Are there some spots more prone to agricultural risk? So maybe during harvest or something else. And yeah, that's it. So big thanks to everybody, because when we capture here, we have to count about 150 or 200 people just to be able to take 10. So, and after that, that's quite yes.
There's a seagull up here. Okay, we have time for one question. No? Okay.
Not really lots of results. So we can talk about the whole project after that.
Okay. All right, thanks, Guillaume.
It's a really small one, but
yeah.
Sorry. It's about the vegetation of the litter. Like you said, you have no idea about it, but like no idea at all, or like did you notice something? Maybe it was just like.
For the moment, not really, because we found litter in a wheat. It was about 20 centimeters high, but also we have some clues that maybe there is a litter inside some maize. It was about 1 meter and 50. Right, so I know. Really not know. You have no idea.
Okay, thanks. Okay, so the final speaker in our session is Brett McClintock, who's going to be talking about multi-state diffusion models for inferring behavior-specific habitat selection.
Thanks, Richard. I was hoping you were going to say this gentleman's name. I'll apologize to all of our wonderful, gracious French hosts when I say Langevin in my American accent. So apologies for that. And my talk today, I'm going to focus kind of on telemetry data, but this model can be used with other types of data, including capture and recapture data. But I'll focus on telemetry. So habitat selection and utilization distribution is often used to identify critical habitat, which is important for the conservation and management of not only protected species, but pretty much all species. And these types of things are often inferred from telemetry data using some form of what's called a resource selection function, which is this thing here. It's kind of like logistic, and you usually identify some important habitat covariates, and then you try and estimate the coefficients associated with those covariates, where positives suggest they prefer that covariate and negatives suggest they don't like it. But typically behavior is ignored, and that's going to be the focus of my talk today. Is we may not always want to be ignoring behavior. And this is just kind of a toy example where when you have telemetry data, the top row here represents kind of what we have as researchers. We often have some sort of a track. You can't really tell what's going on just looking at those points. And then maybe you identify 2 habitat covariates that you think are important. Now, in this example, there's 2 behaviors that the animal is exhibiting. This could be like resting and foraging, or breeding, non-breeding, whatever kind of states you want to envision. And they use the landscape differently based on the behavior they're in. So this is the pattern, the utilization distribution when they're in the first behavior, and then this is utilization distribution when they're in the other behavior. Now, we don't observe these, of course, right? We just observe what's on the top row there. Now, if you were to ignore behavior, this is the type of inference you would make about space use. This is the utilization distribution. And then these are the true underlying state-specific utilization distributions. And when you ignore them, you get kind of this amalgam of the 2. You know, it's sort of the ignored utilization distribution kind of looks like the utilization distribution for state 2. But if you notice the scale here, the coefficients are completely uninterpretable. They're worthless. So that is what can happen when you ignore behavior. in these types of analyses. So how do we incorporate behavior into habitat selection? What's most commonly done is we just ignore it. And there are cases where that may be okay, but it often can be problematic. The folks that have done this have often done a two-stage approach, where in the first stage, you try to identify the different behaviors. That's often done with like a hidden Markov model or something like that. But that usually ignores habitat. It just looks at the movement properties. And then in the second stage, you then like do some sort of like step selection function or something like that, conditional on the state. So you do separate ones for each state. But the problem with that is it will underestimate uncertainty because it doesn't get the state uncertainty into the analysis. And it also can conflate the movement and selection processes. So the third option is to use an integrated multi-state habitat selection analysis, and that is rarely done. But I'm going to propose one way to do it today, and it involves the habitat-driven Langevin diffusion, where this scary-looking thing up here is a stochastic differential equation. I'm not going to go into the details too much, but in words, what this is imagining is that your animal is just this ball rolling along a hilly surface, and that hilly surface is defined by the habitat covariance. So the ball will roll down into favorable habitat, and the ball will not want to roll up into unfavorable habitat. Okay. And the nice thing about this model is its limiting distribution is the standard form of a resource selection function. Okay. So the microscopic rules of movement scale up in time and space to the utilization distribution. And this was introduced in 2019 by Théo Michelot. So continuous time models can be scary, but in reality, often what we do with these types of models is just discretize them to make them more easy to work with, right? So the model may look a lot simpler now if we just use a discrete approximation, where we can see it's just really a random walk where the movement is guided by this hilly surface. So it's just a marble rolling along that surface. And then we account for the time interval between our observation times. And Clark Rushing gave us a nice introduction to continuous time models yesterday. And then we have a habitat selection coefficients. And the only really tricky part is you have to calculate the gradients of these covariates. So they need to be continuous and have continuous first order partial derivatives. So once you get your head wrapped around that, it's not that difficult to envision extending this to multiple states. We can just make all the different parameters state dependent. So now we would have where the sigma parameters are speed, we now make that state dependent. And then we can also make our habitat selection coefficient state dependent. So then conditional on the state, you can move at your own speed and scale and follow different habitat characteristics. And then you also have your own state dependent utilization distribution for each state. So if you're really interested in foraging, you could just identify the foraging behavior and then get the utilization distribution for foraging, for example. And then it gets a lot easier and we recognize that this can simply be embedded as the observation distribution in a continuous time hidden Markov model. So I really don't need to spend too much time on this, hopefully, after Clark's talk yesterday. So yeah, all we're doing here is we're taking our hidden Markov likelihood and we're embedding the multi-state Langevin diffusion into the observation process. And everything else is the same from Clark's talk yesterday. So I'll just do a quick example here. These are 3 stellar sea lion tracks in the Western Aleutian Islands of Alaska. These have been used in a bunch of other resource selection type analyses, so that's why I selected them for this example. Michelot et al. Looked at these data and included several covariates related to bathymetry, slope, and distance to shelf or distance to site. And in their single state model, this was the resulting utilization distribution that they estimated from the model. And this isn't being critical. This is saying though that they like land. I mean, this is a central place forager, right? So they have to leave land, go do what they really want to do, and then go back, right? So to me, this looked like an example where it might be handy to account for those different behaviors and maybe get at something a little more interesting out of these data, because we know they need to go back to land, right? Central place forager, yeah. So I expanded the analysis a bit and brought in a few more covariates. I wanted to use depth, slope, depth by slope interaction, and then distance to site, because they have these rookeries all over the place. So those are the distance to the nearest rookery, and then a quadratic term of distance to site. And the reason for that, I'll explain in a minute. So this is what the model looks like. We don't have to spend too much time on this. We basically have 4 states that we have a central place forager, and I wanted to capture outbound, foraging, inbound, and then the haul out state. And the haul out state is when they just kind of hang out on land and don't move very much. And that each of those states can have their own habitat selection coefficients and their own speed or scale. And then I combine this with conductivity data, which is just wet dry. It's a binary covariate indicating whether or not the animal is wet or dry, and that helps identify the haul out state. And then the last thing I did was I made the state transitions a function of distance to site. And the reason I had that quadratic term in there was so it would help capture, like, once, you kind of want to get away from your central place, but then eventually you're going to want to come back. So that's to help them from preventing from swimming off into space, basically. So that's what that quadratic term is for. Yeah. So this is the big slide, I guess, of the talk. So we see that by breaking it up into several states, the outbound and inbound states kind of capture that the fact that it needs to get away from the central place and then come back. And then what we found is really interesting is this one. So it's the foraging state. And this shows that the favorable habitat is associated with these offshore slopes associated with like submarine canyons and other underwater features that are thought to attract prey concentrations. So it actually has a more biologically meaningful explanation there once we account for the fact that this is a central place forager. So just to wrap up, so I think I'm running out of time. This model is in our package Momentum now. It can be used to calculate those nasty gradients for those covariates, so you don't have to worry about that. And then there's functions for fitting and simulating from the model. And there's further details of it in the vignette in the help files. And this is just an example of the simulation component where this is a single state model here, we kind of just end up with a random walk when you simulate from the single stage model. But the multi-state models produce this kind of characteristic central place foraging movement. So it's good for simulating too. So lastly, this is, to my knowledge, this is the first way to do this in a single stage. And it's also can be readily implemented in user-friendly software. It can also be integrated with other data types. So in the example I showed, we use conductivity data, but it can be combined with dive data or accelerometer data. And that's really helpful for distinguishing states that have similar trajectories. And then, as certain behaviors are often more relevant to conservation and management, hopefully practitioners can use this to help get at what they're really interested in. And there's Paul Langevin with another famous physicist. So thank you.
Okay, we can take a couple questions.
Thanks for your talk. I would like to know if you know how sensitive could it be your discretization to the discretization scheme. I mean, if I seen you did an Euler discretization of the future time given the past. If you do some mix between the present and the future, and that would that improve something or the variance to be controlled or in some way or not?
Well, I'm not sure I totally understood that, but you're talking about the length of that discretization, like how long the steps are between?
The length is the discretization, but also how you discretize the equation in itself. I mean, if you do a Euler scheme or a Crank-Nichols scheme or implicit schemes, it may change some things. I know in some simple linear models, if you have an Euler scheme, some things explode, the variance with the time. But you don't have that problem here, and I'm interested in it. How you know if...
Well, I've done simulation. I didn't talk about the simulations here. So this is just an simple Euler discretization scheme. And yeah, it does break down once that length of time gets to be too far between your observations. So you do need to be careful about the observations being like regular enough relative to the behavior that you're interested in. So it's really about behavior. So if you have infrequent observations relative to the behavior that you're interested in, this thing will blow up. You can't just use any, if your observations are really far apart and you're trying to ask a really specific, fine resolution question, you're not going to do it.
Thank you very much.
Yeah.
Nice talk. Am I right in thinking that you could put in a term that would deal with sort of a persistence in a discrete Markov model where you might have one of those habitat covariates might be just continuing in the same direction that you are and with some sort of, and might that, I wonder how that would.
Sure. That might characterize the behavior when you're foraging and things like that a lot better just by a ball that's rolling, doesn't roll in the same direction.
Yeah, you could also just put a correlation term in there. That won't mess up the diffusion. In other words, yeah, you gotta be careful when you mess with the diffusion portion, like the habitat, the gradients and all that stuff. But you could, where the equation had like mu of t plus 1 is equal to mu of t. You could just put a plus and then a parameter times u of t minus 2 minus u of t minus 1 or whatever, yeah, and get at that correlation. And that wouldn't affect like the stationary distribution. Yeah. Yeah.
Great, thanks, Brett. I was wrong. We've decided to add an additional talk that was missed yesterday. So our final talk, I think, for the session will be by Priyanjana Ramani.
Thank you. Sorry about that. 12 minutes and then you can get your coffee. So I didn't get to present yesterday and the organizing committee was kind enough to stop me in today. This should have been in causal inference for management. This is a side project that I started when I was working on my master's and which I didn't really think would ever see the light of day. So I'm very excited to talk about it. This is probably a figure that many of us have seen many times. When you identify a conservation threat, you conceptualize that threat, you plan actions and monitoring systems before you actually implement them. And then it's called the adaptive management framework because you're continuously using the monitoring data to analyze, share, and adapt your intervention. In practice, however, that does not always happen. Huge conservation policies, interventions, and legislations go through without going through these processes. So in the context of India, let's say in 1972, the Landmark Wildlife Protection Act was passed. In 1973, we launched Project Tiger, and we now have more than 50 tiger reserves all over the country. We don't know what would have happened if the Wildlife Protection Act hadn't been passed, if Project Tiger had never gotten off the ground. These are huge questions which I'm not going to try and answer, but I will try and answer a small part of this. Data lets us create counterfactuals. That is, it lets us try and think about what would have happened if this policy hadn't happened. So I call this the program evaluators toolkit. There's propensity score matching, which was talked about yesterday. There's also regression discontinuity designs, difference in differences, and my personal favorite, synthetic control methods that let us look at the actual causal, let us get at the causal impact of an intervention. And that's a good thing for policy because first off, it's good to know what if the program hadn't happened? Why did the program work if we have that kind of information? Did another factor other than the intervention actually cause the result? And in terms of replicability and scalability, what effect would a similar intervention have? This helps us allocate often scarce resources, reach conservation goals. It promotes more efficient decision making, and it builds an evidence base of what works. So counterfactual thinking and impact evaluation have been part of other policy fields like nutrition and economics for a really, really long time. But as of 2006, they were practically non-existent in conservation. However, by now we have had at least 2 systematic reviews and meta-analyses which shows that these methods are actually becoming part of conservation research and methodologies. However, there's a big gap in this. Protected areas, which are arguably the best known conservation intervention, are often not evaluated. So they're often, whether they work or not, are often inferred from pre and post comparisons or comparisons between protected areas and unprotected areas, anecdotes, case studies, and so on. And by definition, for example, comparing a protected and a non-protected area is going to lead to all kinds of bias. This brings me back to synthetic control methods, a method which I first encountered in economics class. This particular paper, Abedi et al. 2007, looked at the effect of an anti-tobacco policy which was implemented in California on smoking rates. Now, the thing is, California is a single treated unit. It's a very unique, very distinct unit. It's not like any other US state. No US state is like any other US state. Instead, using economic data, the authors created a synthetic California using income, retail price, beer consumption, and so on, and looked at the effect of the policy over time. And the real California and the synthetic California are almost equal in 1970, and by 2000, they've diverged. And similar methods are being used in conservation, which is extremely exciting. So this particular paper looked at the effect of the COVID-19 lockdown on forest fires and therefore forest loss, and found that as a result of the lockdown and quarantine, fires increased by a huge amount. So a literature review that I did on this, however, yielded just 26 results. And most of the research came out of Latin America. And particularly, I noticed a dearth of evidence from India. And of all the various interventions that looked at the effect on, all the studies that looked at the effect of various interventions on forest loss using SCMs, nothing about the establishment of protected areas and what effect they might have. So, quick review. In India, we have a protected area network. So the most protected are tiger reserves, which I already mentioned. After that, you have national parks. After that, you have wildlife sanctuaries. So if a wildlife sanctuary or a national park gets upgraded to a tiger reserve, what effect does that have? So my question, let's start with, do tiger reserves prevent deforestation in India? Or at least that's what my question should have been, but I committed the cardinal sin of being very methods driven. So here's my actual question. Can I use synthetic control methods to see if tiger reserves prevent deforestation in India? Okay. I forgot to mention, this is an extremely data hungry method. You need time series data for every single year in your study period for every single unit. So I relied a lot on open source data. Hansen et al. Has this amazing data set on loss of forest cover from 2001 to I think now 2022. I used shapefiles of the boundaries of protected areas from the Wildlife Institute of India. And then again, all of my predictors also needed to be time series variables. And the Indian Meteorological Department has information on rainfall, which we know is correlated with forest cover loss. Or at least gives us an idea of the environmental factors. And then to get at human impact, I used the massive livestock, again at a district level, as well as per capita income and other factors. And my treated unit was a tiger reserve that was declared in 2011. It was upgraded from a wildlife sanctuary, and it is home to the Sholega community who have lived there for hundreds of years. And using livestock, rainfall, per capita income, and so on, I tried to create a synthetic BRT tiger reserve. So the dashed line is my synthetic control, and the not dashed line, I'm forgetting what it's called, is my actual observed data. And you can see that before 2011, before the creation of a tiger reserve, they're actually following very similar trends. However, post 2011, there is this spike in deforestation in the synthetic version of the BRT Hills Tiger Reserve. Now, if I was to just look at the data for the BRT Hills, if I was to do a before and after comparison, what I would find is that the policy didn't have any effect, right? Because it roughly stays the same. If I look at the synthetic data, however, I see that maybe, if I'm to believe these results, very, very tentative, but there appears to be an avoided forest loss caused after the tiger reserve was established. So this is the difference in the synthetic and the real BRT tiger reserve. These are the weights that the algorithm, this is tidy-synth from R, gave to my variables. And as well as up here, you have the different wildlife sanctuaries and national parks that were used to create the synthetic BRT hills. And finally, the placebo effect, my placebos are very, very faint, but you can kind of make out the red line is, of course, the real BRT. So these are still very preliminary results, and I'm looking forward to including more district level data to match to my protected areas. It's kind of hard to find at such fine scale, but this is an ongoing project. I'd love to hear feedback. And I think this is important because, well, we know a lot about protected areas. We don't know as much as we should about the effects that they are having, which can inform policy. So I'd like to thank the Euring committee for allowing me to present this, all the folks at the National Center for Biological Sciences, where I did my master's, and all of you for listening. Thank you.
We have time for a couple questions.
Hey, thanks for a great talk. I was just thinking that one of the most common methods I've seen to evaluate effectiveness of protected areas is site matching. And my intuition is that that uses the same information to distinguish the impact of protected areas as your synthetic controls does. And I was wondering whether you've thought about comparing those, or what your guess would be about how the two of those would compare in terms of being able to identify an impact.
Yeah, that's a great question. So one of the papers that have actually looked at this from, or the kind of one of the few papers that I know that have looked at this in India specifically is Kurgi and Karanth, I think 2019. And I think a great next step would be to actually come, so they used matching, one-on-one matching between tiger reserves and wildlife sanctuaries. And I think that would be a great next step to kind of compare, to see whether, they match or not, if this is actually adding anything, or it's just, we already have what we need to do this kind of thing.
Thanks. I'd love to talk to you more about that.
Sure.
Any other questions?
Thanks for the talk. It was really interesting. I'm wondering what you did to kind of validate your synthetic reserve, because I noticed already in the before period there was a difference between the observed and the simulated data. So did you use some methods to make sure that it should behave sensibly?
Right. So if I can just go back to, I'm not sure I can completely answer your question, but I'll try. As you said, absolutely, the trends are different in the pre-intervention period. I mean, the numbers are different in the pre-intervention period as well. Part of that, I think, is because I just do not have enough predictors yet, and I will keep adding to them. But if you look at this box down here, this compares the metrics for the real BRT, the synthetic BRT, and the entire non-treated sample. So for example, for rain, you can see that it's 124 millimeters for the entire sample, and it's just 73.8 millimeters for BRT. And then when you look at the synthetic BRT, that's 74.9 millimeters, which is a lot more similar. So that's kind of one of the validation methods that tidy-synth uses. And hopefully I will be able to get a closer match as this work goes on.
Great. Well, let's thank Priyanjana and all of our excellent speakers in this session.
Like, no, or one other presentation.
So we'll just push everything back?
Yeah, I think so.
Okay.
But we were quite well, actually, yeah, with the timing and these things. But when I saw this new presentation, I was like, no, we're right on time. I want my like click.
Hi. Hello.
I'm Michelle.
Hey.
Nice to meet you.
Nice to meet you.
Your section chair looks after you.
Okay.
How do you want to be introduced?
I mean, just Richard. Yeah, that's fine. Yeah,
okay.
yeah.
Miss, I wasn't sure who was still by insurance.
Usually
Richard.
Richard, yeah.
Okay, very good.
Yeah.
I can handle that.
Okay. Yeah.
I'll let you get off that.
Yeah.
Yeah, I know. Yes, we need to set. And I feel like I've never really over there, and also we forget that it should and so what's the next Yeah, we're doing check it. There's going more courses in this is happening later. So for that we do checking that now and next manual surveyors. So we're ready to see how Yes. Yes. Yeah. And I guess it's exactly. So thank you Yes. We are, let's say, so we are able to achieve. So yeah, so that's it. So we are and then for them to explore the traffic ones, they need to go. So it's a bit of a, and then we can check it out and say, we don't think this is a good idea. And then there is some exactly there is some dialogue around that. And if they are really far off, we'll say no, we will accept this. If they are, it's acceptable that we think this is better than looking it, then we will be yes. Because the interpretation is if you're then we will vote. Then I whole thing will yeah, it is. Yeah. So that's something we have to we are doing this research organizations, so it's a data we will spend 5 minutes. Yeah, so that's also something we are developing. Yeah, exactly. That's also something we are it's one of these things. Ideally, I don't know that if I was to simplify, but then thanks to 2 years ago, like even though someone's investigation that we're in a future that is station processing. Yeah, so we use this kind of obvious I was very certain every day,
sharing stories not really good.
Yeah, but it's always worrying that type of distinction. How interesting is data and data practical. It's one of the really classes people that design yeah, exactly. Both. Yeah, okay, sure. Could do it.
Yes, and also ways where we as a resource, that's not that we do that.
Berlin. Yeah, I am, but my position is just yeah, so that was three. That's what just finished. Yeah. So now, but I'm presenting the stuff. Especially when you've only got 11 minutes to record 12 minutes. It's better 12 minutes. Right? Yeah, but I'm not sure. They offered yeah. Yeah, I mean, the weekend, and then you get some. I was in Montenegro for like we got here. Unseasonably cold. Totally unusual. It was below 10. It was colder there than it was in so we I mean yeah, exactly. So now it's
real time. Okay. So I will tell you one question, two questions, depending on the time that we have. And when no more question, I will do something like this. Okay. Okay. And I will talk. The only thing is that I will tell you at the end of the talk, like 1, 2, or no questions. Or...
Okay. And for questions in the Zoom,
try to prioritize the Zoom question because it's not that is doesn't make sense to do something. I think that Aurelian is gonna like telling you about this kind of things. Okay, Aurelian, are you paying attention to
I can do it.
Okay.
But we are very few.
Okay.
Thank you. I was wondering whether I should tell people to be quiet.
And then I stop when you
Okay, thank you. We're going to start the session on connectivity now. And so we have 4 very nice talks. And we're going to start with a virtual talk by Matthew Gonnerman.
Hi, everyone. I'm Matt Gonnerman, and today I'm presenting research from my dissertation out of the University of Maine, where we looked at how we can use individual-based models based on multiple data sources to estimate population connectivity for wild turkey. When we manage wildlife, we often use administrative boundaries that are based on political, social, or practical limitations. Unfortunately, animals don't really care about those things, and they move according to their own fitness needs and their perception of the landscape that they occupy. This can lead to a conflict between real populations and the boundaries we use to manage them. As an example, harvest regulations are often based on some rule set dependent on abundance within management units, and this can lead to a mismatch between the administrative boundaries and the population ranges. Take this map of Maine's wildlife management districts here on the right. This same set of boundaries are used to manage deer, turkey, moose, among other species, and are unlikely to be appropriately sized for each. Additionally, if immigration rates are unbalanced among units, this could impact population dynamics and would require knowledge of animal movements to match harvest management decisions with underlying population processes. For turkeys specifically, aspects of their ecology in Maine may lead to a greater than expected chance for large-scale movements by individuals. Turkeys must contend with harsh winters and shortened nesting seasons compared to their core range, which requires them to make seasonal movements between 2 ranges to attain the necessary resources to survive the winter and reproduce in the following spring. You can see examples of such movements here on the left, where blue indicates a wintering range, green indicates a seasonal movement, and yellow and red indicate pre and post nesting respectively. To provide some context, on the right, I have the National Land Cover Database depiction of the same area, where green is forest, yellow is agriculture, and red indicates urban land use. As you can see, turkey movements can cover a range of land use types and vary dramatically in scale within the same area. If turkey movements are directed by local landscape characteristics, to what degree is the landscape influencing where turkeys go? And if these movements occur with great enough regularity, what are the implications for movement between management districts? These movements occur immediately before spring harvest, so do we need to account for them when we set harvest regulations? To answer these questions, we need some way to assess turkey movements across the state. Often, the motivations and consequences of animal movements are understood in the context of functional connectivity, a component of landscape connectivity which describes the degree to which a landscape enables or impedes movement. This approach deals with fine-scale movements of animals and how they interact with landscape characteristics. Decisions can be broken into propensity to initiate movements, but within the matrix, and settling decisions that terminate movements. Each of these characteristics may have distinct and specific motivations that can influence animal movement dynamics. At broader scales, we can also look at migratory connectivity between populations, which assesses to what degree animals with the same origin end up at the same destination. For example, if we have multiple populations of birds that breed in the same area, how many of these birds that migrate south end up in the same wintering grounds together? These two approaches differ in both the spatial and temporal scales at which inferences are made. Functional connectivity is concerned with a continuous fine-scale process, usually within a single season, while migratory connectivity focuses on broad-scale discrete decisions that often occur across seasons. To provide insight into the impact of turkey movements on their distribution among management units, I built a simulation model that predicts how land cover characteristics influence the initiation and termination of seasonal movements for wild turkeys, as well as simulates their likely movements between their winter and spring ranges. I then used this model to assess the connectivity of turkey populations and predict movement amongst management regions. Specifically, I use an individual-based model of turkey seasonal movements to describe the transfer of individuals between WMDs. The IBM describes our understanding of the functional connectivity across the landscape, and the results from many simulated turkeys, otherwise called agents, can be used to infer migratory connectivity. Here I have a diagram showing the major components of the model and how they are used. I will go over this I will go over this broadly first, and then I will move through the submodels individually. On the left, we have our data inputs, which shows the flow of various data types within the model. We used turkey nest and harvest locations compared to capture locations to describe the propensity of individuals to initiate and terminate seasonal movements. We used hourly GPS tracking data to train behavioral parameters of an IBM, and then calibrated those parameters using the nest and harvest data. We additionally used the GPS locations to build a habitat suitability surface, which would inform the simulated turkeys' decisions during their seasonal movements. Finally, we estimated WMD level migratory connectivity using the calibrated IBM, where turkeys were placed on the landscape according to population estimates produced from a separate integrated population model. So propensity to initiate movement was estimated using a logistic regression, whereas settling decisions were more similar to a step selection function, so we used a conditional logistic regression. Here I have the estimates from these models plotted across the state, where initiation is on the top, settling is on the bottom, males are on the right, and females are on the left. From these results, we identified that female turkeys were consistently less likely to initiate movements and more selective in their settling decisions compared to males. Based on these results alone, we may expect males to have a greater rate of WMD border crossings compared to females. We then used the results from these models within the IBM to probabilistically initiate and terminate agent movements. All agents were initiated with behavioral parameters which govern their movements within the matrix. For our agents, behavior was defined by how important habitat was to their decision, how far they tended to travel, and their tendency towards straight line movement. Once a seasonal movement was initiated, agents selected their next location from the available locations within their perceptual range. Locations were weighted according to an agent's behavioral parameters using habitat information and the distance and turning angle relative to the current agent's location to define a weight for each. Agents continued to make decisions and move until either they probabilistically ended their movement or the simulation ran out of time. While we initially built the model based on GPS data, this information was from a very small portion of the state and was unlikely to encompass movement behavior exhibited by all turkeys in Maine. To broaden the scope of the model and better describe movements across the state, we used the nest and harvest data with approximate Bayesian computation rejection sampling to calibrate prior distributions from which agent behavioral parameters were drawn. In brief, GPS data was used to create an initial prior for each movement parameter, and a set of agents were initiated at the capture locations of each nest or harvest location with behavioral parameters generated from this prior. The IBM was allowed to run to completion, and all agents that ended seasonal movements near the associated nest or harvest location were retained to generate a new prior for the final model. On the right, you can see the calibrated movement parameters, where the solid black lines indicate the initial uniform prior based on GPS data, and the red dotted line is the final pooled distribution we used to simulate WMD connectivity. Once the submodels were created and calibrated, we placed agents at starting points on the landscape consistent with estimates of turkey densities in each WMD. We then ran the model and recorded the starting and ending locations for each agent. From these two locations, we could examine multiple aspects and consequences of seasonal movements. Here we have the total number of turkeys exchanged between different WMD pairs. The thicker the line, the more turkeys that moved between a given pair. And as you can see, the vast majority of exchanges between WMDs is occurring in the southern portion of the state, although this is partly due to the greater abundance in these regions. And these movements are not perfectly balanced among WMDs, and this which results in variable levels of change in abundance caused by these seasonal movements. So here you can see how dramatic these changes are as a percent of initial abundance. The greater negative change is indicated by blue and greater positive change by red. As you can see, it appears that WMDs in the southern portion of the state are either neutral or losing turkeys to movement, while the rest of the state has more mixed results. So now we have an idea of how turkeys are moving among WMDs in Maine. How does this affect the proper management of turkeys here? Well, for one, it appears that the magnitude of change associated with movement warrants some adjustments to population models to account for immigration and emigration among WMDs. It also is likely that these movements will need to be taken into account for harvest management, especially if the loss of movement is additive to the loss due to harvest. We also need to be aware of potential source-sink dynamics emerging from these movement relationships, which may change the ability to reach a desired management outcome. For example, if managers want to reduce turkey abundance in WMDs with a net gain that have a net gain due to movement, it may require a larger increase in harvest than would otherwise be called for. Finally, the distribution of these net changes are largely in line with our current fall harvest regulations and management objectives set by MDIFW, except in the northeast portion of the state, where the state agency wishes to grow turkey populations, but currently a limited fall harvest and net loss due to movements may inhibit reaching those goals. Before I end, I'd just like to quickly acknowledge all of my funding sources. If you have any questions, I'll happily answer them now, but you can also reach me at any of these 3 websites. Thank you.
We have time for 1 or 2 questions. Well, Matthew, I'll ask a question. Have you considered the impacts of edge effects of turkeys moving from other states or from Canada down, and how that might affect the results?
We on the northern border with Canada, that is less of an issue because their populations are even less dense than ours. So that would be, there's probably only a small number of turkeys along that Canadian border. New Hampshire, definitely there could be some flow back into the state there. But we don't have any estimates of turkey numbers in New Hampshire to work with. So that we had to leave that part a little bit open-ended.
All right. Any other questions? Okay, well, thank you. Next we have Mylise Kerbalek, who's going to be talking to us about mapping connectivity from non-invasive surveys. Thank you, take it away.
Good morning, everybody. So I'm going to present you our work on mapping connectivity from non-invasive survey with spatial capture recaptures. And we are focusing on the Pyrenean brown bear population. So first of all, what kind of connectivity are we talking about? We are talking about landscape connectivity, which was defined as a degree to which landscape facilitates or impedes movement among species. As habitat loss and fragmentation has been major concerns in conservation policies, more and more work and policies say to talk about connectivity. For example, the US government in March published this memorandum and asking federal departments and agencies to implement conservation policies on connectivity. Europe financed the restoration of connectivity. Also, the IUCN published guidelines on connectivity. And in France, the National Management Plan for the brown bear population asked to restore connectivity for this population. So let's focus on the brown bear population. This population is distributed over France, Spain, and Andorra, and it was almost extinct in 1995 with only 5 bears remaining in this population. To avoid its extinction, 11 bears were translocated from Slovenia, and now this population is recovering with 76 bears detected last year. So now that this population is recovering, we wanted to map connectivity, and more especially, we wanted to quantify to which extent roads impede inside home range movements. Usually what we use is GPS data, but here the monitoring of the population is based on capture-recapture data. So here the black crosses represent the traps, which are air traps for this population, which are sampled every month from May to November. And we wanted to use spatial capture-recapture models to analyze this kind of data. So imagine that you have an area of traps where 2 bears are living, the orange one and the blue one. They can be detected. So here, for example, the orange bear is detected as 2 traps and the blue bear is detected only 1 trap. We repeat the survey, and at the second sampling occasion, the blue bear is still detected as the same trap and the orange bear remain undetected. So from this detection data, we can feed a half normal detection function, meaning that the further you go from the activity center, the less likely it is to detect the bear. However, with this formulation of SCR model, we don't account for the fact that the landscape may affect the probability to detect the bear. And for example, if this bear in orange doesn't cross the road, it will affect the probability to detect the bear on the other side of the road. So how we do that? Usually in SCR model, we use the Euclidean distance, meaning that if we want to compute the distance between the activity center of the orange black bear and these traps, it's simply 5. If we account for the fact that there is a road, the cost is increased to 20, and the best way to link these 2 points is not necessarily the straight line, but we can compute all possible paths and keep the one with the minimum value, which is not necessarily the straight line. And it's also known as least cost path. And from this model, we can have an explicit estimation of the resistance parameter that we call alpha. So go back to our population. Our goal was to estimate connectivity from our capture-recapture data using the R package OSCR. But the problem we encountered was that the monitoring of this population is mainly concentrated in areas where there are already bears. So we wanted to expand the study area. And to do so, we integrated depredation data. So we assumed that all depredation that occurs in the Pyrenees since 2010 was the distribution of livestock in the Pyrenees. And then we aggregated that to a 5-kilometer grid. So in other words, the sheep flocks are our traps, and the detection occurs when a bear kills a sheep, and we are able to identify the bear responsible for the damage. So here you have the distribution of bears, and as you can see, integrating depredation data allowed us to expand the study area, to have more detection of each individual, and also, like, as you can see in Aragon, to detect all the bears that were missing from the previous monitoring. The resistance surface that we put in our model was the length of road in the Pyrenees, and you can see here the Mediterranean coast, and also Andorra have a high length of road that could impede the movement of brown bear in the Pyrenees. So now the results. The estimated resistance parameter was 0.4, which is positive, meaning that the road are limiting brown bear movement, but it's quite complicated to understand what it means for the population. So if we assume that we have an activity center at this pixel, then we can compute for all pixels in the landscape the probability to use each pixel. You can put another activity center and another pixel with a higher density of road, and as you can see, their home range are shaped by the road network. Then we can assume that we have an activity center in each cell of the landscape, and we obtain this map by summing all the previous maps. As you can see, in red, it's high potential connectivity, meaning that it's easier for bears to move through the landscape. And the blue part is a low potential connectivity and allow us to identify barrier to movement. As we can see here, the Mediterranean coast and Andorra have low potential connectivity, but also here at the western part of the brown bear coast, there is also a barrier to movement that can impact the expansion of the population. We can have a realized measure of connectivity by weighting the previous densities with the previous connectivity with the density that we have estimated in the spatial capture recapture model. However, these values are quite difficult to understand and also to understand what it implies for this population. So there is another way to map connectivity for this population. We can go back to our potential connectivity for our two bears, and here we can divide the utilization probability of each pixel by the sum of all probability to have the utilization distribution around this activity center. Then we can compute the kernel at 95% to have a delimitation of the home range of the bear, and we can also compute the area of this home range. As you can see, in high potential connectivity area, home range seems to be bigger, as in a low potential connectivity area, home range is restricted by road and smaller. We can do the same and compute for each pixel the area of the brown bear, and you can see that we have the same pattern as before. That's great. And we also have a measure that it's more easy to understand for this population. So to sum up, RCM models are quite data hungry. There is a lot of data to be applicable, especially here, but they are really flexible to the monitoring you have for the population. Also, SCR models allow us to estimate connectivity from non-invasive genetic sampling, and it's especially convenient when you don't have GPS data to monitor your population. Thank you.
Are there any questions?
Thank you for your presentation. It was very clear. I was wondering if you know how much accounting for the roads reduced the total estimated home range of the bears. Did you, because it feels like when you have roads, then the estimated home range is reduced because of this barrier. Do you know overall how much does it affect the estimated home range?
It's affected especially when we have a high density of rows. So we can compare here for two bears, and it was reduced up to twofold.
Thank you for the really cool talk. Just a small question about, are you thinking about including other types of variables for this model? So far there's roads, but are you thinking of like any other variables that could affect home range or connectivity? I don't know that much about pairs, but I think mountains, and at some point maybe they might not want to go to really high altitude places. I don't know, just a question.
Yeah, we could have integrated as many variables as we wanted, but here for this model, we choose to integrate forest cover, human densities, and elevation on the density of the point process. Though these covariates are integrated on the density part of the model and not on the connectivity, but we could have chosen to put this variable on other part of the model, because in some part of the Pyrenees, you have area where you have both a river, a road, housing, so it may be the accumulation of barriers that limit brown bear movements.
And we have a question from the internet. The question is, nice talk. Why does Andorra act, or does Andorra act as a barrier sink on this landscape? It seems only 1 to 2 activity centers could fit there. Andorra?
In Andorra, it's just there is a lot of housing and roads. So with the covariates that we implement in the model, there is no possibility to have a bear living there.
Okay. Well, thank you.
Okay.
Next, we have Killian Gregory, who is going to talk to us about an integrated framework to combine migratory connectivity and demographic data.
Yep. So thank you for the introduction. I will talk to you today about connectivity at a much broader scale that was nicely introduced in the first talk of the session. So as they move across countries and continents seasonally, migratory birds draw connections between different parts of the world. These connections between areas or populations have been gathered under the name of migratory connectivity. Migratory connectivity is key to understand how localized events, spatially and temporally, in the migratory cycle may affect the dynamics of the whole population. Would it be like changes in resource availability, the emergence of a disease, or localized environmental pressures and changes? The toolbox to investigate migratory connectivity is actually quite large. Basically, every type of data that can be used to track animals through space can be used to draw connectivity patterns. This includes, of course, the classic bird banding databases, tracking technologies, but also some spatial assignments based on isotope or genetic signatures. To a lesser extent, some other types of data have been used. But what is important here is that given this diversity of data, people have started to combine them to make the best of their respective strengths and try to make more representative data sets. And among all the combination techniques, there is one that has a really high potential. It is the integrated modeling. We've been talking about this the whole morning. So I'm sorry, I will push some open doors for a lot of people here, but I want it to be clear. By integrated modeling, sensu stricto, I'm talking about the combined analysis of different data sets within a single framework, which means that you have various submodels that are processed simultaneously and share information on at least one shared parameter. If we take a very simple theoretical example of 3 data sets, 1, 2, 3 here, informing on basic parameters, alpha to epsilon, integrating them allows to extract more information about the shared parameter and also to better identify some parameters as well. This has been used quite a lot in population dynamics studies, of course, and recently it has started to being used in migratory connectivity studies. So, in an attempt to try and bring together different domains of ecology that have been considered separate until now, this appears to be a very promising tool and promising direction to investigate. This is what we tried to do here. We tried to combine an integrated population model based on the work of many people who are in the room right now, and integrated population model also. And well, we tested this on a simulated dataset and a real dataset. I will come back to this later. So to go really quickly Through the architecture of our model, it's really simplified here in this conceptual scheme. You have here a very basic integrated population model that combines data about population counts and capture mark recapture in the breeding season. It's important to say this for migratory species. This integrated population model gives information on various demographic parameters in green and also observation detection probabilities. And on the other hand, you can do the same for the integrated migratory connectivity model. And this integrated migratory connectivity model revolves around one central parameter, that is the transition probability between breeding areas and non-breeding areas. This is basically our migratory connectivity estimate. So I will not dwell too much on the details here, but tracking data, resighting of banded birds in destination areas, the recovery of dead birds in the destination areas all inform on this transition probability. And what is also important here is that capture mark recapture data in the breeding season can also inform on this transition probability. Thanks to a neat little trick that was used by Clark Rushing in a previous paper, you can link the survival in the breeding season to the survival in the non-breeding season using these transition probabilities, basically the proportion of individuals moving from one breeding area to one destination. Once we have this link, the connections between the integrated population model in green and the integrated connectivity model in blue appears simple, actually. So this was applied to two datasets. As I told you, I will first present the real dataset because it conditioned our simulated data. We use data of the Eurasian curlew, which is a wadder that breeds in almost the entirety of Europe and also stays in Europe for the non-breeding season, but it moves slightly more to the western shores. To fit our quite scarce connectivity data, we had to delineate large clusters between which to investigate migratory connectivity. But still, it was enough to develop the model as a proof of concept. So we had three big clusters between which we investigated the movements between the breeding and non-breeding season, a northeastern cluster in Europe, northwestern, and a southern cluster. As for the data we had, most of it came from the Euring databank. Yay, that's the theme of the whole conference. We had capture mark recapture in the breeding season, re-encounters and recoveries of banded birds in the non-breeding season, and also some tracking data provided by nice collaborators. The population dynamics data we had was quite limiting, but again, still enough to develop our model as a proof of concept. We used BirdLife International population trends and tried to fit them in the integrated population model. So of course, the simulated data mirrored exactly this. We had 3 breeding and non-breeding clusters, the same types of data, and it was just known and more homogeneously reported in the entirety of Europe. Having this on the simulated data allowed us to check the precision and accuracy of our estimates in the model by looking at the standard deviation and the root mean square error. So to have a quick peek at our results here, some of our results, you have the transition probabilities, first thing to look at. On the top, you have our proxy for accuracy, the inverse of accuracy. Below, you have our proxy for the inverse of precision. And for the 3 models, the integrated population model in blue, the integrated connectivity model in green, and the combination of both in red in the center. What you can first see here is that obviously the integrated population model does not estimate the transition probabilities. It was not meant for this. But the combination of both models does not perform particularly better than the connectivity model. Here does not lie the strength of our model. However, when we look at demographic estimates, the combinations seem to perform at least a bit better than the connectivity model, but a lot better than the integrated population model we had in terms of both precision and accuracy. And this was also the case for the real data. You have just a sample here because it's quite large otherwise. You have the transition probabilities between cluster south in the breeding season and bird being in the same cluster in the non-breeding season. Again, you can see that the combined model in red does not perform better than the connectivity model. But for some basic demographic parameters, at least we were able to identify a bit more the parameters, especially for survival. This allowed us to draw this kind of connectivity patterns, again, very simple because you only have 3 large clusters, but we can see that curlews breeding in the northeastern cluster tended to move quite diffusively to the northwestern and southern cluster, whereas birds from the northwestern and southern cluster tended to stay in the same place in the non-breeding season. Yeah, we call this a gradient of connectivity strength. So to quickly discuss this, our model were able to estimate both demographic parameters and connectivity parameters that were quite consistent with the literature. We slightly overestimated the fecundity, but the integration of both types of data mainly benefited to the estimation of the demographic parameters. This is a nice property of the integrated model, and probably the fact that the migratory connectivity parameters did not benefit from this was because it was already strong for the size of the clusters we had. Also, we're able to benefit from another property of the integrated population model that was mentioned at the beginning of the day. We're able to estimate some parameters, or at least identify them a bit better, parameters for which we had no explicit data, fecundity in this case. So this is still work in progress. Of course, it could be improved on both sides. For the population dynamics study, we would benefit from having more detailed population counts, obviously, and try to make the model better fit to the life history traits of the species. As for the connectivity model, what would be great is to obviously decrease the size of the cluster, increase the number, to draw more interesting patterns for conservation purposes, and also relax some of the hypotheses of the model. But we are now at a time where many people advocate for the collection of more data in migratory connectivity studies. We need more data to know where birds go and what impact their movements have globally on their distribution and population dynamics. So we already have nice tools to combine them. We just need to make the best of these tools. And having flexible frameworks to allow us to understand the connections between migratory connectivity and population dynamics would allow us to include more information about the whole migratory cycle of the species, some maybe environmental correlates to understand these dynamics, and even allow migratory connectivity to vary across time along with population dynamics. With this, I would like to thank my supervisors and all the people who helped and provided data for the work, and thank you for your attention. I'm happy to take any questions you have.
We have time for 2 questions.
Great talk. Were you able to look at level of bias in the region-specific or season-specific parameters?
Well, I only have very basic parameters at the moment. I just have basically survival in the breeding and non-breeding season. So this would need for the model to be a bit more completed. But this is indeed a really interesting direction to investigate. Thank you.
Thanks, that was a very interesting presentation. I'm just wondering, do you have any idea about where the main limitations are in terms of the types of data we need to extend the use of these models?
Well, of course, we would take anything we have. But the main limitation is to be determined by the true objective of the study. If you want to try to connect migratory connectivity and population dynamics, of course, you would need both of them. And the type of connectivity data you can collect and use highly depends on your study species and the area that it occupies. So in this case, probably, well, I cannot tell actually. It depends on the species. Sorry about that.
Okay, thanks very much.
Great talk. Can you remind me how you selected your regions? Because it seems like your results are really dependent on how you chose those.
That's true. So we have to first do a preliminary study and have a prior information about where the birds go and where they come from. Usually, people do this based on just the expertise they have on the species, but I think it would be beneficial to first tag some of the individuals and have a look at where they go, or do a broad scale study using spatial assignments. Isotope data is great for this in the right regions because you can easily get huge information about a lot of different individuals. So we would need some preliminary studies to truly identify the clusters between which to look at the connectivity. Yeah.
And now we're going to have Lisa Viola talk to us about animal demography and movement and Banali's eagle.
So hello everyone, and I will present you some of the results of my PhD thesis, which is about animal demography in movement. I will more talk about the individual spatial component and not really on the demographic part of the Bonnet eagle because it's still in progress. So individual in a population varies on several traits. They have different individual characteristics in terms of age, sex, physical status, experience. They also show different individual behavior, and they can have different individual performance, like the survival or breeding success. So all these different between individual is what we call the individual heterogeneity, and all these different traits can be influenced by environmental and habitat conditions. One of the individual behaviors that we can study on population, it's the individual movement. So life history of individual involve movement at different temporal and spatial scale, such as the daily movement within a home range, the dispersal between territory or between population, and the migrations. And today I will focus on the daily movement. So basically, individual movement, it's a trade-off between the energetic costs that the individual need to spend to perform the movement and the benefits the individual will have by performing this behavior. And this trade-off between the energy cost and the benefit will affect the body condition of the individuals. And by that, movement can have a direct impact on the survival and fitness of individuals, and so can have major consequences on population dynamic. But what can explain why two individuals of the same species or the same population move differently? There is a lot of hypotheses, and mostly maybe they have different individual characteristics, or maybe they don't face the same environmental condition like the weather or habitat heterogeneity during their lifetime, and so have different movements. And my aim today is to test this hypothesis on the French population of the Bonnet eagles, the big chickens that you see here. So adults of this population are highly territorial. They live in pair all their life, during all their breeding life, on the well-defined spatial space that we call a home range, where they do all their daily tasks, like foraging, but also all their breeding activity. So we are lucky because we have a really nice data set with 48 adult individuals that were equipped with a GPS tag and coming from 30 different territories. And also the French population was intensely monitored from the last 30 years. So we have a really good understanding of their demography and dynamics, as well as survival and breeding success. With the equipment of the GPS tag, we are allowed to know the home range of all of our individuals, and we were really surprised to see that we have a really high heterogeneity of home range inside these populations. So as you can see here, we have all the home range size in our population, and it's really different depending on the individual, with a variation coefficient that is around 61. So it's quite huge. And for example, if you compare the biggest home range and the smallest home range, you can see that the biggest home range is 1,200% bigger than the smallest. It's really huge. So we have really a large differences in type and shapes among territory and individuals. So the home range that you see here is a result of the movement of individuals and their position in the space. So we can ask if the high heterogeneity that we observe here is a result of different movements among individuals within this population. To assess this, we study 3 proxy movement behavior, such as the daily median distance from the first resting point of the day, the daily sinuosity of trajectory, and the daily proportion of time spent in flight. And do movement differ among individuals? The answer is yes, and a lot. So here you can see the median daily distances, mean daily median, the mean daily sinusoidity, and the mean daily proportion of time in flight by individuals. And as you can see, we have a lot of difference between our individuals too, with the variation coefficients that are more than 30 for each of our proxy of movement behavior. So why movement behavior are so different between individuals? Maybe you remember the hypothesis that I talked about earlier. It's the time that I test this. So are this movement in this population impacted by environmental condition, habitat characteristic, and individual characteristic? And there is yes, but as is often the case in science, not as we expect it to be. If we take the environmental condition, we can see that movement behavior of bony legal are strongly impacted by environmental condition. So here you can see the effect that we have for the daily median distance, for the rainfall, wind, and mean temperature. And as you can see, there is a really strong effect. It's barely the same for the proportion of time in flight and the sinusoidity. But at contrast, movement behavior of bony ligand aren't really strongly impacted by individual characteristics. We find a little effect of the experience of the individual as well as the reproductive status of the current year and of the previous year. But it's very weak, and it's even weaker if you compare with the weather effect. The differences that we see are mostly due to the expression of different behaviors through the year. For example, here you can see the difference between the male and female for the daily median distance. So the female in pink during the brooding in the region barely don't move, they stay on the nest, compared to the male that do all the hunting. It's why they have such a different daily median distance. And after the pledging on the cheek, the male and female hunts together, so they have quite similar distances. So we are happy because our results match the biology of the species, so it's cool. But one of the effects that surprised us the most is the effect of the habitat characteristic. So it was really in contrast to our predictions. Habitat characteristics have a very little effect on the movement of the individual, as you can see here with there is barely no effect. So we were thinking that the habitat will have a strong effect because there is a high heterogeneity of habitat inside the home range. There is a different proportion of cultivate land area, forest area, inval area, and scrubland area between the different home range. So, and these habitats are not used the same by Bonelli eagles. So we were thinking that it will affect strongly the movement, but habitat heterogeneity does not strongly affect at all the movement behavior of Bonelli eagles. So to conclude to that, we observe in this population a really high heterogeneity of territory and movement behavior among individuals that can have effect on the population dynamics that we might not understand yet. Individual Bonelli eagles movement are really strongly impacted by weather condition and less that we expected by individual characteristic and by habitat characteristic. And it raised a lot of more questions. So I talk about the heterogeneity of habitat among territory. So we can ask if habitat characteristic doesn't affect movement of population. Do habitat use maybe differ among individuals within this population, and can be explained what we have such difference home range. And last but not least, it's a central point of my PhD. What are the consequences of this heterogeneity of territory and behavior on the population in the dynamic? Do movement behavior impact breeding seasons? And for now, I don't have the results, but only primarily, and I can say that, as it's often the case in science, not as we expect it to be. So thank you for listening to me.
We have time for some questions.
Great job, Liz. My question is, because your population is so well studied, do you know the age of the birds? And did you see any differences related to age?
So we know the age of mostly all our individuals that are tagged. So we don't, in the model, we don't put the age directly. we put the experience because it was really linked to the age. So yes, there is when, for example, with the daily median distance, when a bird pass a long time in his breeding sites, they become more efficient. They have more shorter distances, and so things like this. So we can talk about it more if you want. But yeah, we mix them together, and the experience also allowed us to have the recruitment of individuals in the breeding sites. So the first year of experience, it's the first year of recruitment. So it was better to use the experience more than the age.
Hi, it was really nice. I just wonder, like the home range of the different population, it's stable across the year?
There is a little bit differences between the internuptial and breeding seasons. So during the breeding seasons, it's a little bit bigger. But when you have a bird that have a really small home range, it will be small during internuptial and breeding season too. It's but yeah, you have a slight differences. And if you compare the home range of a female during the breeding season and the male, it will be completely different because they stay on the nest.
Well, I have one question. I wondered, you found a big effect of the weather covariates, but I'm presuming that analysis was on sort of individual days.
Yeah.
I wonder whether you see the same important differences when you look across space as opposed to just through time and seasonality, and whether you've thought about that.
It's in progress.
Okay. Well, great. Thank you so much for that great talk and for all the great talk.
Right?
Yeah. All right.
So same place. Follow the plans.
Is the second I sent to Olivier Jimenez yesterday update.
Want to check?
I just want to
I can do it for you. Just to check that nobody is
Okay. The less you make me responsible for it, the better.
Yes. Sure.
Just one question, two questions, or not, like this. No more questions. Okay, great.
Are you going to make an announcement?
No.
Welcome back, folks. Welcome back. My name is Michelle Kissling, and I will be your session chair for the session titled NATO Dispersal and Migration. So to kick off our session, I'd like to welcome structure animal model for quantitative genetic decomposition of variants in seasonal migration versus residence.
Thank you. Hi, everyone. So climate change is altering seasonal environmental viability. And one major concern is the increase of extreme climatic events, such as storms, droughts, or floods, which can cause mass mortality and reproductive failure, and hence dramatically impact population growth and increase extinction risk. But can populations overcome such changes? What will be the longer-term consequences? Here, we need to focus on key traits that link the environment to fitness, where some phenotypes can mitigate or avoid the negative impacts of environmental perturbations. So different phenotypes will differentially affect survival and reproduction. This is natural selection, which will change phenotypic distributions within generations. And if there is additive inherited genetic variation underlying phenotypic variation, there may be an evolutionary response to selection, changing phenotypic distributions on longer terms. And phenotypes may also change directly in response to environmental variation through plasticity. And there may even be selection and evolution of plasticity. So if we want to predict eco-evolutionary dynamics, we need to quantify all these components and their combined effects. And one key trait that, through which animal populations can respond to environmental variation is seasonal migration, which is the reversible movement between breeding and non-breeding locations across seasons, and which allows individuals escape harsh conditions occurring in winter. And this trait can be viable within populations, leading to partial migration, where some individuals are resident throughout the winter, while others migrate at some point. And I studied this trait in a partially migratory population of European shags breeding on the Isle of May in Scotland. where thousands of individuals have been ringed since 1963, which allowed us to collect detailed pedigree data. And since 2009, we have tracked their locations year-round during weekly reciting surveys along the coast. So we have information on the phenotypes. We classify individuals as residents when they are seen in the Isle of Man area and as migrants when they are seen elsewhere. And obviously these recitings provide us with survival data. From this, I compiled 2,500 encounter histories of adults on which I'm focusing. And to analyze these encounter histories, I devised a full annual cycle multi-state capture-recapture model, allowing inference on phenotypic expression and accounting for spatio-temporally varying detection. So every year starts with the breeding season, when all the individuals are on Isle of Man. Then individuals may transition between resident and migrant states across 4 winter occasions, and then they all go back to the Isle of Man for the next breeding season and repeat this cycle. And obviously, they may die in between occasions, which allowed us to analyze survival differences summarized on this graph of annual survival probability against year, with residents in red and migrants in orange. And we can directly see 3 major drops that concurred with extreme climatic events in the form of severe winter storms that led to mass mortality. And in 2 of these years, there were huge survival differences between the 2 phenotypes, indicating strong selection for migration and against residents. So now if we want to investigate the eco-evolutionary response to selection, we need to appropriately conceptualize the quantitative genetic architecture of the trait. For dichotomous traits like migration versus residence, this can be rationalized under the threshold trait model. Here, the trait is assumed to be underlaid by a continuous latent variable termed liability, and if it is below or above a certain threshold, theta, the individual expresses respectively the resident or the migrant phenotype. So any individual will have a certain liability intercept resulting from genetic effects and permanent environmental effects, and will deviate from this intercept due to temporary environmental effects, which can make the individual switch phenotype if it crosses the threshold. And to estimate these variations on the liability scale, I developed a joint capture-recapture animal model. Here, we still make inference on phenotypic variation using our multi-state capture-recapture model utilizing reciting data, and we couple this with a quantitative genetic animal model enacting the threshold trait model, which utilizes pedigree data to disentangle inherited genetic variation from other variation encompassing environmental variation. And the key output of this is a decomposition of trait variants into multiple components. So what did we find with this? We found non-negligible additive genetic variants, which is a potential for microevolution of migration in response to selection. And the corresponding fraction of total variance in liability, so the heritability was about 8%. The permanent individual variance was 69%, which is a very large variance fraction, mainly attributable to permanent environmental effects lasting from early life plastic development. This gives an overall repeatability of liability of about 77% and a temporary environmental variance of 23%, representing rapid liability responses to current environments. Now, if we look at the population level changes in mean liability effects through time, we directly see with the mean additive, so the inherited genetic effect, that it increases right after the extreme selective storm. So we detect an immediate evolutionary response to selection that drives a background increase in liabilities. But if we look at the mean permanent individual effect, which is non-heritable, we see much bigger changes, notably strong changes right after the extreme storms. And these lifelong individual effects that drive short-term dynamics in liabilities. But there is something else behind the story. And I want to draw your attention towards this interesting property that variation in liability intercept can generate variation in phenotypic plasticity. Indeed, individuals with an intercept close to the threshold, they will be likely to cross the threshold if there is a small environmental perturbation and hence switch phenotype. While those far from the threshold, they will be unlikely to switch for the same magnitude of environmental perturbation, and hence they will be less phenotypically plastic. In fact, any gene and environmental effects on this liability scale must interact to generate a discrete phenotype. But we can quantify this variance of interactions. And I solved the integrals allowing full variance partitioning in migration versus residence, and we retrieve the modus heritability, the large permanent individual variance, and the considerable temporary environmental variance. But all these fractions, they were smaller compared to the liability scale, because now we have this large emerging variance in phenotypic plasticity, which is due to the interaction between temporary environments with genes and permanent environments. And to conclude, I wanted to stress that CRAMs are very useful for dissecting eco-evolutionary dynamics in the wild. They allow integrating the estimation of selection with variance partitioning while accounting for detection bias. I showed additive genetic variance in migration versus residence and immediate evolution in response to selection due to extreme storms, which is pointing towards a potential route for evolutionary rescue against the increase of extreme climatic events in animal populations. I also showed very large non-heritable permanent individual variance, pointing towards a crucial role of plastic development in early life, shaping migration in adults and hence the response to extreme storms. And I highlighted an inherent gene by environment interaction variance in stressful traits, which is implying a fascinating interplay between evolution, plasticity, and selection, which now deserves deeper investigation. And that's it. I thank you for your attention.
Thank you, Paul. Do we have any questions?
That was a very interesting talk. Have you thought about, one of the hypothesized reasons for partial migration patterns is also social structure or, dominance hierarchies where either, less dominant individuals may move or things like that. Have you thought about how there might be an interplay to social position or how that might change over time or whether these effects are variable through time or just, anyway.
Yeah, indeed. I mean, this might potentially be the case. I have no clue about this in sharks actually, but definitely it could play a role. Maybe individuals that have a better social position, they're able to stay in the residency area during the winter and have access to the nest sites earlier than the others, and they exclude the other ones. That's definitely a possible hypothesis, but yeah, I have no clue about this.
Thanks for your talk. It was really interesting. I was wondering if, looking at the proportion of individuals that are resident or migrant, or the probability that an individual switches between one or the other, do you have density dependence in there at all, where if you have higher numbers of residents, you might be more likely to be migratory?
Yeah. So I haven't shown these proportions, but just to tell you, we have roughly 50% of full year residents and 50% of individuals that migrate at some point, among which half are full migrants throughout the winter. And So we don't really know if it is density dependent because we only have 10, 12 years actually in total now. And we had one big event with this selection events that halved the population, and it did not result in a very strong effect on migration versus resident, but still after that, there was a drop in the number of migrants, actually. Am I correct or not? No, actually it's the opposite. So there was a drop in the number of residents, which is what I showed, linked to the liability that is linked to migration versus residents. But yeah, we don't really know about the actual effect of density dependence.
Great, thank you, Paul. I'd like to welcome our next speaker, Rita Fortuna, and the title of her talk is Using a Multi-State Capture-Recapture Animal Model to Estimate Additive Genetic Variance in Early Life Seasonal Movement.
Thank you. Hi, everyone. So if you enjoyed Paul's talk and you would like to spend some more time on this topic, don't worry, I will repeat everything again, but in a less nice way. But thank you, Paul, for the introduction. And yes, so I'm here to show you how we're estimating evolutionary potential in the seasonal movement, but focusing on the early life period, so on the juveniles. Oh, sorry, ahead. And so I'm sure all of us are aware in this room of the severe consequences that rapid environmental change can have on animal populations, such as changes in seasonal climatic conditions. And so one of our greatest challenges today is to understand whether animal populations can persist in the face of these changes. And one of the ways that this could be done is through microevolution. And so this means that there would be a change over a short period of time in the allele frequencies of the population, which will favor traits that can allow individuals to escape or to endure these harsher conditions. And there are two important things that need to be met for microevolution to occur. The first one is that these key phenotypic traits need to be heritable. And the other one is that the expression of this additive genetic variance needs to occur at critical life stages of the individuals where we know that selection is occurring. And so the trait that I'm here to talk about today is seasonal migration. And this is a trait that is widespread across taxa and influences individuals' survival as well as reproduction by allowing them to temporarily escape conditions that may not be ideal or even tolerable. And one interesting aspect of this trait for ecoevolutionary studies is that populations are commonly partially migratory, which means that there are year-round residents and seasonal migrants in the same population. And this will, of course, lead to different selection on migrants versus residents with an obvious direct effect on population dynamics. And a key point here that I want to make is that, as we saw, seasonal movement strategies, or whether you're a resident or a migrant, can be quite repeatable in adults. And so this suggests that there may be evolutionary potential for this trait during early life. For instance, if one or the other strategy is selected for in this early life period, or whether it becomes fixed. And so this is what we're trying to look at, the rapid evolution of seasonal migration during the early life. And we're using this great system, the European shags, as a study system, more specifically the population that breeds in the Isle of May, where they are considered to be residents. And we know from the adults and the work that Paul has been doing that adults are partially migratory, so about half of the individuals will migrate during autumn and winter along the coast of Scotland, sometimes even further than that, while about the other half will stay resident in the Isle of May. And recently, we've also been quantifying what happens with the juveniles. And what I can tell you so far is that we know that they can migrate soon after fledging, and a slightly higher proportion of juveniles will be migrants, but there are also some juveniles that stay at the residency site. And so with this, framework, we wanted to understand whether there is potential for microevolution in this trait in the early life by quantifying heritable genetic effects. And to do this, we gathered two types of data. So similar to what Paul showed, we have access to breeding monitoring occurring in the Isle of May since the early 80s, which allowed us to build a pedigree of this population with 6 overlapping generations and almost 16,000 individuals. So we hope powerful enough to detect additive genetic variants. The other type of data that we had needed to be related to the strategies of the juvenile. So are they resident or migrant in their early life? And to know this, we used resightings of the juveniles at the residency site, as well as places where they're known to migrate along Scotland. And we had informations of the ring juveniles during their first year of life. So with this information, we could build their capture-recapture histories, which will tell us whether they were resident or migrant. And to put this information together, we worked in a multi-state capture-recapture animal model framework, which I'm explaining now in a bit more detail. And so in classic animal models, what we want to do is to decompose the variation in a trait and understand how much of that variation is explained by heritable genetic effects. And we usually do this with continuous distributed traits, so normally distributed traits, but in this case, we have a binary trait, categorical, so whether the individual is a resident or a migrant. And in this case, what can be done is to work in this threshold trait model framework, where we assume that these two alternative phenotypes will be expressed when the values of this underlying liability scale, in this case, liability for migration, are below or above a certain threshold. And so all the variance decomposition that comes from the animal model will work on this liability scale. At the same time, we were relying on reciting data. And so, of course, as all of us are aware here, this is associated to an imperfect detection process that needs to be accounted for. So we worked in a capture-recapture model framework, where we had 5 occasions during the first year of individual's life, where we attributed them to different states depending on their phenotype, so whether they were seen as resident or migrant, as well as their location, so more or less frequently observed locations that we expected varied in detection probability. At the same time, what brings everything together, so the animal model information with the capture-recapture model information, is that the probability for individuals to transition between these states is informed by the phenotypic expression of their liability to migrate. Okay, so after explaining how this model works, I think we're ready to look at some results. And I have to tell you that this is work in progress, so I would really appreciate any feedback you might have on this. And in this plot, what you will see is the variance components that we estimated on the individual's liability to migrate, with a specific focus on the additive genetic variance. You will also see that we estimated these at 2 instances, so in their first autumn and then in their first winter, and you will later hopefully understand why. And in this y-axis, you see the variance explained by each of the components with a posterior mean and 95% credible intervals. And when the plot shows up, you will also see some percentages, which will show you the proportion of variance that each of the components explains over the total variance. So let's look at it. Autumn. So what we can first see here is that we have an additive genetic variance on their liability for migration in autumn that is clearly estimated to be non-zero, with a mean around 0.6, and which translates into a heritability of 15%. So 15% of the variation in their liability to migrate is explained by additive genetic variance. We can also see in this plot that belonging to the same brood seems to explain little variation in their liability for migration, and that there is a strong proportion of permanent individual effects. Now let's look at the winter. So what changes between these two time periods? Here instead, we see that additive genetic variance is less or clearly less estimated to be different from 0, which translates into about half of the heritability. Thank you. And with an even stronger proportion of the liability for migration being explained by these permanent individual effects. Okay, so what does this mean in terms of potential for rapid evolution of this trait? As I told you before, we need two important conditions to be met. So we do find substantial heritable genetic effects. We find that they are mostly expressed in autumn. What about selection? And what we know from parallel studies in survival selection in the juveniles is that the strongest selection episodes, so juvenile mortality, is much higher in winter than it is in autumn. And it's also when we see the greater differences between the survival of juveniles that are resident and migrant. So in conclusion, even though we find substantial heritable genetic effects on early life seasonal movement, the potential for microevolution might still be limited because there seems to be an asynchrony between when selection occurs in their first year of life and when additive genetic variance is expressed, or what they do being explained by inherited genetic effects. And so this ultimately shows the importance of looking at ecoevolutionary processes at finer temporal scales, which can be quite challenging to do. So yes, that's it on my side. Thank you for listening, and I'm happy to chat about this anytime.
Great talk, Rita.
Thank you.
Do we have any questions?
Hi, thanks, Rita. It's a really great talk. I was just curious about, maybe you said it and I missed it, but what do you put in the individual effects? Is that like the weight of the bird, the growth rate, the timing of the season? Or?
Yeah, those could be all very potential and nice effects to put. So for now, we just don't put anything. So we just see what is the proportion of the variation that is explained by this individual being this individual. And so what this work shows actually is that, so the motivation to look at the juveniles is because we found this strong permanent individual effect in adults. And so we thought maybe it's during the early life that there is something happening that becomes fixed. And what we see is that in their first months of life, when they can migrate, there is already a strong permanent individual effect. So we think that this could come from permanent environmental effects even before this period that we're looking at. So it could be parental effects, it could be related to their nest, so the cohort. So we haven't modeled yet what these effects could be, but that's something we want to do.
I just have a follow-up to that. I was thinking of timing of egg laying, and if you had investigated that at all, so birds that fledge sooner are more likely to be more decisive.
Yeah, that's been on my mind, and I think that's one of the most likely things that we have to explore first, because I mean, their fledging dates or egg laying dates, they are not very widespread, so they are quite synchronous, but there is still some variation, and so this could definitely be one of the explanations for it, also because we see some variations across cohorts, and so this could be related to that. Yes, definitely. Thank you.
Great, really neat stuff. Thank you very much, Rita.
Thank you.
Our next talk is by Charlie Souk and is titled "A Multi-Event CMR Analysis Applied Reveals the Influence of the Natal Colony for Age-Specific Movement Patterns of Yellow-Legged Gulls."
Hi, so I'm Charlie Souk. I start my PhD contract in November at Montpellier at the laboratory MIVEGEC, and today I will present to you marker capture models that allow me to study the variation in movement in yellow-legged gulls. So among the animal kingdom, the seabirds are known to perform extensive movements like migration or dispersion. And there is a lot of factors who can influence this seabird movement, such as age, sex, weather, resource, etc. So all these movements and the factors that influence them are important when we work on conservation ecology or epidemiology. And the general question that interests me is what are the key factors that influence the seabird movement and how do they modify the movement pattern of the gulls, of the seabird. So as a biological model, I use a yellow-legged gull. So it's a gull with quite common around the Mediterranean area. It's a colonial breeder, so it's easy to work on. And you have other characteristics, like it's an opportunistic species who live close to the humans, so he forage on dumps, landfills, and he carry a lot of pathogens who can be potentially dangerous to humans, like the West Nile virus, bacteria with resistance to antibiotic. So there is a concern to work on his movements to prevent the disease risk. And it's a partial migrant, so like the European shags of the two previous presentations, there is some of the individuals who migrate and others who will stay sedentary. So it's a good model for study these movements. So based on the assumption that the environmental factor will change at the geographical scale, like we think that the yellow-legged movement will vary between colonies if the environment have a link with the movement. So for investigate this hypothesis, I used all the ringing data sets from 5,000 individuals who has been ringed in the Southern France in 14 colonies between 1999 and 2004. So you can see here all the colonies. I aggregate them in a different region. So there was a region of Camargue, the region of Marseille, and the region of Hyères. So for give a sense of a scale between the colonies are more far away from each other, there is like 200 kilometers. And all this ringing bird who has been ringed when there was shift has been recited over 10 years by many bird watcher. So after this step, with this data set, I wanna made multi-step marker captures because I wanna study the probability of movement and not only the probability of survival or detection. But the difficulties with this data set is that there is no reciting protocol. It's opportunistic reciting. So the data are continuous over space. So I have to make a different geographical site that you can find here. Like this, I can estimate a probability of movement between my different sites. So the first site was a colony. It's like 50 kilometers around the natal colony. The second site in red was the Mediterranean basin, in blue the Atlantic coast, and for the rest of Europe. So the second difficulty is that the data are continuous over time, so I have to choose to cut the time for my capture occasion, and I choose to cut it in semester according to the phenology of the species. So for make this marker capture model, I have to test the assumption and do a goodness of fit models. But during the goodness of fit models, we find heterogeneity in the data. But we cannot know at this stage if it was a survival heterogeneity or detection heterogeneity. But we made a positive association test, and we find that the source of this heterogeneity was detection heterogeneity. So for summarize, it's just like there is an individual who is more thin than other. And so for correct this heterogeneity, we create two classes of individuals with different detection probabilities. So after this step, I have begin my selection of models. So I prepare all the factors that can influence my different parameters of interest. So I put in the general model the effect of age. I tested a different typology of age class. Parameters relative to time, like season and year, the natal region, and I test different aggregation between all my region that I was talking to you before, the reciting site. And on top of that, I add the detection heterogeneity that I was talking to you in the previous slide. So with this general model, I made a declination of 47 models with the surge. Then I launched data analysis. So the model who was selected by this selection of model have a survival affected by age and natal region. We have a movement affected by age, season, and natal region, and a detection affected by reciting site, time, and the heterogeneity of detection was selected by the model. So what is important in our result is that the movement and the survival was affected by the age and the natal region. So the typology of age class was being selected was a typology with 2 age class, with the juveniles, 6 months, less than 6 months years old and 6 months old, and the older individuals. So for the effect of the age, the juveniles move more than older individuals. And for the natal region, the Camargue individuals was more sedentary than the one who's of Hier and Marseille. So in the natal region, the group of Marseille and Hier was pulled against Camargue in the model section. It was selected by the model, sorry. So just to look at this estimator for the movement probability of the juvenile during the 6 months after the fledging. So you can see here the probability of movement from the birthplace to the other geographic site. So in the green bar is the probability of staying around the colony, so to be sedentary. In pink to go in the Mediterranean basin, blue to go in the Atlantic coast, and for the rest of Europe. So at the left you have the juvenile from Camargue, and here the juvenile from Marseille and Hier. So what you can see is that the juveniles from Camargue are more likely to be sedentary than the one from Marseille and Hier, who go more further during this stage. So we can ask the question of why this difference of movement pattern between natal regions. So what an idea is that it's the poor environmental quality that inciting girls to migrate further. So for this point, we have a good point, because like we can look at the juvenile survival and maybe use it like as a proxy of the environmental quality. And the juvenile survival in Camargue was much higher than in near Marseille, who was moving more. So it's a good point for this hypothesis, but it has to be more study after. And the other question was why there is this individual heterogeneity to detection. So one hypothesis is like there is other research teams that are work on the specialization on the foraging of the gulls, and maybe it can be a factor that explains this heterogeneity of detection, because there is gulls who forage more in landfills, in dumps, than others who are more foraging at sea. And so this it can create a disparity in the detection, because the bird watcher go in dumps for seeing a ring gull, for example. And the conclusion, the biological conclusion, is that the young bird may spread avian disease more frequently than older individuals, and this tendency may be influenced by local reproductive success, which in turn may depend on a lot of environmental stress, like lack of resource, pathogens, contamination by pollutants. So currently we begin a GPS monitoring program, and we have a current ringing program. So these two things in parallel to the monitoring of the reproductive success and the biological sampling will permit me to study deeper the links between gulls movement and the environment, with two main questions: the effect of reproductive success on bird movement, and the effect of anthropogenic food like dumps on migration strategy. So thanks for listening. This work has been published just recently, so you can find all the details here. Thanks. Feel free to ask questions.
Great. Thank you, Charlie. Do we have any questions?
Thank you very much for this great analysis. Did your heterogeneity parameter and detection allow for different season heterogeneity between the Camargue and Marseille, or was it fixed to be the same distribution of heterogeneity between the two?
We test the detection probabilities with the natal region, and it has not been selected by the model, even if the detection heterogeneity was not taken in account. So we think that there is no difference in the detection of the Camargue individuals and the Marseille individuals. If it's it's a good answer or not, I don't know.
Very interesting talk again. When birds are detected in the other regions besides the one where they came from, do you have a sense of whether they're typically detected at the same location, if they're detected multiple times, or if they're showing up at multiple dots? Because that might get at some underlying issues if there's some capture heterogeneity that goes to zero, and maybe that explains the survival, but perhaps you see them when you see them at many dots. I don't know if that makes sense.
Yeah, sometimes in wintering area, for example, there is one who go in the same dumps and who is reciting for a few weeks sometimes. But like my capture occasion are from our semester, so they count like one time in the models, like if it was in one time. So I don't think it can be affect the detection heterogeneity at this level.
Great job, Charlie.
Thanks.
I would like to welcome Richard Chandler, the last speaker of this session. His talk is titled Directional Natal Dispersal in a Trailing Edge Population of Black-throated blue warblers. That's a tongue tie.
Okay, thank you very much. So I'm going to be talking about some work today that's part of a larger project we're doing studying the dynamics of trailing edge populations. And so trailing edge populations are populations at the receding edge of a shifting distribution. And so for the black-throated blue warbler, that would be these populations down here in the southern Appalachian Mountains. Before I get started, I want to acknowledge Heather Gaia, who's the graduate student who's taken the lead on this work. Unfortunately, she couldn't be here to present it. Okay, so our study area is here in Western North Carolina in the southern Appalachian Mountains. And the reason we're focusing on this area is because, as we've demonstrated, this is actually an area where you have, it's kind of a hot spot for trailing edge populations. So we see that there's over 20 species with their southernmost populations occurring in this region. And that actually represents a fairly large proportion of the total avifauna. So it's around 20–25% of the birds in this area fall into that category. So if you haven't been to this area, you should visit. It's quite nice. This is the Blue Ridge Mountains here, quite near the Great Smoky Mountains National Park. If you go to these forests, they're characterized by these dense understory of rhododendron and mountain laurel. And if you look at where protected areas are, at least for the East Coast of the US, you would say, oh, well, we're doing pretty well here. And these are all protected areas, some form or another. And so there's quite a large amount of this forest that's in a fairly natural state. However, like everywhere else, we're seeing climate change impacts. This is a trend in mean air temperature in early spring and summer. We don't see a trend in average precipitation, but we've seen an increase in variability in precipitation. So this is a variance in precipitation, and what you can see is that's been increasing. So we have more years that are warmer than average and more years that are quite wetter than average. And we also have some evidence that these changes are impacting these populations. So large number of species with this very similar distribution. Most of the ranges in Canada and the northeastern US, but these populations down here at the southern range margin appear to be declining. However, this is just breeding bird survey data, and the breeding bird survey doesn't do a great job of covering this region. So you have to take this with a bit of a grain of salt. What we want to do is really understand not just if populations are declining, but what are the mechanisms involved, the demographic processes. And so we have many hypotheses. We've been trying to attack each of these in different ways. But we're really taking a demographic approach. So how does each one of these processes influence survival, reproduction, and movement? And today I want to talk primarily about this movement piece, which is really one of our central questions, because if these populations are declining because these populations just continue to move up slope and they're eventually going to go locally extinct, that has very different implications than if these birds are able to track optimal conditions and move northward with climate change. This work has been done in collaboration with folks at working at the Hubbard Brook Experimental Forest, where they've been studying black-throated blue warblers for quite a lot longer. At both sites, the historical design was to have these 3 long-term plots where you try to band every single bird, find every nest, traditional marker recapture work. So we have, between these 2 sites, it's 2 range positions. There's 6 sites at 3 different elevation positions at each one. And we have marker recapture data going back to 2002. This comparative demographic work was recently published in this ecological monograph, and I'm not going to talk about all the details, but the main point I want to mention here is that, as you would predict, if there were climate change impacts on the populations at the southern range position, we see at the high elevation site relative stability since 2002. Whereas at this low elevation site, the warmest site down at the trailing edge, this population actually went locally extinct. So just in about a 10-year span, the population went down to just a single pair. The home ranges were getting larger and larger, and the demographic work was discontinued because there were so few birds there. We continue to check on it every once in a while, but there's basically no reproduction there anymore. And then at our middle elevation plot, we're seeing more of a steady decline over time. So this paper talks about the survival and recruitment processes influencing this. But because it was non-spatial traditional marker recapture design, we weren't really able to disentangle the effects of movement and dispersal in particular. So that's what we're trying to focus on now. So more recently, since about 2014, we've expanded the study design. So rather than just having these large study plots where we do very intensive work, shown here by these 2 rectangles, we've added point counts. So we do kind of more extensive work over this climate gradient. So this is just the color scheme here is just showing elevation, which is a proxy for our climate gradient. And so we're trying to span that with our point counts, but we also have these constant effort misnetting sites now. So each little red cross, so there's like 20 red crosses in this cluster is a misnet. And so we go to about 20 sites every year spanning this gradient. So we have these 3 different types of data that we're using now to get a better spatial coverage of this region. Okay, so what do we see? Well, studying natal dispersal for these small passerines is quite challenging. They're not like big shag and gulls that are maybe easier to track over time. And since we've started this work, we've banded over 2,000 nestlings. So we find these nests, we band each nestling. So find quite a lot of nests and band quite a lot of nestlings. Of those 2,000 birds, 24 have been rediscovered in subsequent years. So that might look like a very dismal sample size, but we're really proud of it. Because if you go to other places where this work has been done with long distance migratory passerines, they get almost no returns. So just to have some information about the natal dispersal process is new for these neotropical long distance migrants. Okay, so if you look at this, again, we have the climate gradient shown by the colors in the back. So these are the cooler climates at higher elevations, and each arrow, or at least each number associated with it, is a dispersal event. Okay, so what you see is if you look at these birds that were born at the highest elevations in the coolest climates, they tend to stay put. So we see, this 4 individuals moved from this location to this location, not very far. We see some individuals have made long movements up to the higher elevations. Some have gone the other direction. There's quite a bit of noise here. But what you don't see is any long distance movement into these, or movement at all, dispersal towards these warmer climates at the lower elevations. Okay, so that's kind of the raw data that we're going to use to look at natal dispersal. If you look at the adult dispersal, they show much higher site fidelity, and this is pretty well known for these birds. So even though they fly thousands of kilometers every year, they return to pretty much the exact same breeding spot year after year after their first breeding attempt. So usually within 100 meters of their previous nest location. So you see, again, these birds at the high elevation, 89 of the birds, adults banded here, came back to pretty much the exact same place. Okay, so how are we going to model these data and assess whether or not there is directional dispersal, or is it just kind of a random walk movement among years? So basically, we're using a discrete space, discrete time, simple movement model for our maybe not huge sample size, where we're just using this categorical model. So conditional on being born at location S at IT, where did you go your next location at time T? And these probabilities, this is basically kind of a discrete dispersal kernel. We modeled using something like a resource selection function that includes distance from your previous location, age, as well as this climate factor. I'm running out of time, so I'm going to move quickly. We're also accounting for survival, as well as detection probability. So what's the probability that you're found, given that you're alive, given that you occur in this particular location, and given some other factors influencing detection? Okay, so here are the estimated dispersal kernels for the adults. So if you're an adult, the contours here are those climate contours. If you're an adult that bred successfully in this pattern, or bred at all at this location in kind of the warmer area, you're most likely going to come back to the same location. So the probability of returning is highest basically where you were, and it's a fairly symmetric kernel, and we're not seeing any sort of effects of climate. And that's true also for adults that were born at the coolest, highest elevation sites. However, if you look at the estimated dispersal kernels for the young birds, we see that if you're born in a warmer area down here, you're more likely to move towards that cooler climate at the higher elevation. So this is our first kind of evidence of directional natal dispersal. However, if you're already born at the tops of these mountains, at the highest, coolest, wettest sites, you're most likely to stay in those locations. Okay, so to summarize, we are seeing evidence of these declines of trailing edge populations. Based on that work that is in that monograph and this work, we're starting to find evidence that it's really not decreases in survival or necessarily even reproductive performance that are causing the declines at the lowest elevations in the warmest sites. It appears as though it's this directional natal dispersal may play a larger role in these population changes. And so next steps are to try to study dispersal over larger spatial scales and to try to really understand the genetic consequences of dispersal-driven changes in these populations. Many people to thank, but I'll go ahead and end there. And yeah, thanks again.
Great talk, Richard. Thank you. Do we have any questions?
Any thoughts on implications of looking at the short end of the truncated dispersal distances?
Yeah. So I wish there were more time. You know, we have no evidence from like bird banding lab or anything of long distance dispersal in these birds. You know, you don't find evidence of birds being born in like North Carolina ever showing up in, say, Maine or something like that. So we don't have evidence of it. There almost certainly is some long distance dispersal that was never observed. But the way this model is set up, it's basically the dispersal kernel is kind of a conditional dispersal kernel. So it's given that you survive and return to this general study area, where do you go? So it's really like we're studying kind of short distance dispersal within our study area. So if that's independent of this sort of long distance movement process, then I think there shouldn't be any reason for concern there. But that's ideally what we would like to do, is be able to study dispersal at larger scales. Yeah.
What's the sex ratio of birds showing natal final patching? Are you losing one sex?
Yeah, good question. So I wish I had the numbers handy. We do see, it's not clear if it's phylopatry. We're definitely seeing differences in survival, though, between the sexes, so in the first year. So that's still a bit of an open question of is it survival or is it differences in phylopatry? Yeah.
Could it be possible to estimate the number of missing juveniles? Considering population growth, how long the adults breed?
Right.
To have some idea of where are all these guys going, the ones that don't show up?
Yeah, well, we know from other species that most of these guys go right into the mouths of predators, right, when they jump out of the nest, if they get out of the nest at all. So, you know, massive mortality in the first few weeks of life. I think it would be possible to, you know, this is in some ways kind of like a spatial Cormack-Jolly-Sieber model where we're conditioning on, you know, being alive at the initial period. So we're not trying to estimate how many individuals are out there that are entering the population in other ways, but yeah, I think we would have to do some other work to kind of get at more fine detailed information about the early survival process. Yeah.
Great, thank you, Richard.
All right, thanks.
Concludes the natal dispersal and migration session. I'd like to thank all the speakers for great post-lunch talks. And we now have a short break and for 14 minutes. Well, I'm looking at the very precise schedule. Thank you, everyone. I really enjoyed the talk today. Good job.
It was clear.
So impressed.
Je sais pas si, est-ce que tout le monde voit les questions dans le chat? Pardon? Tout le monde voit les questions dans le chat ou c'est seulement les autres et Nelly? Du coup, c'était l'occasion de mettre en DC pour les chats.
Moi, j'ai pas le...
Ah, si, là. Ouais, avec celui-là, non?
Bah, attends.
Merci beaucoup. Bon, ouais.
C'est pas raqué.
Ouais. On va commander pour 100.
On a déjà développé tout le stock.
Non, là, je crois qu'il a le
Ok.
Non, je vais l'avoir sur le site.
I know it's so helpful that you're keeping. Yeah, because we believe that I was writing questions. That's another. And it doesn't need to be changed.
This is the growth over here.
Yeah, so can they sit
I'm gonna be with the time business. So yeah, I thought you already know, but yeah, I will. Yeah. Things I will just let you know, like if 2 questions, just 1 question, and no more question or something like that.
All right. So basically, I have to.
And I would really like to like with the and I think that Aurelia is gonna be with the Switch chat.
C'est quoi le Sherman? Non, non, il y a juste que...
Elles vont apparaître. Ouais.
Elles vont apparaître là.
Ça marche.
C'est tout par let's start.
Hi everyone. So it's now the time for the session on phenology, and our first speaker is Ken Clark, who is going to talk about estimating UK butterfly abundances at varying spatial scales using science count data with accounting for changing phenology.
Yep, that's correct. So yeah, quite long, but there we go. So, okay, for a quick introduction to butterflies in the UK, we've just got 59 species that we count as resident or regular migrants. So the UK is a nation of butterfly enthusiasts. So when there was an apparent decline in them in the mid-20th century, they decided to start the UK Butterfly Monitoring Scheme. So this was in 1976. It started with just 34 sites. But then, as you can see from the map, as of 2018, there are over 1,700 sites across the length and breadth of the UK. And at each site, a transect walk is done, and basically butterflies are counted at the species level, and this is done once a week from April to the end of September. And already these have been used to determine abundance trends out of 58 of the 59 regularly occurring UK species. Sadly, what we've got is that 74% of species are declining in occurrence and 52% are declining in terms of abundance. This is due for a myriad of reasons, such as habitat destruction and fragmentation, as well as climate change, which is often due to a mismatch in the host plant emerging and the adult butterfly emerging. That is what we're going to be looking at. So phenology is seasonal timing of events. What we're interested in is the adult butterfly emergence. So it has been shown that with warming climate, the species are emerging earlier year on year, but there's also the spatial variation to account for. So maybe if you see a species this week in the south of England emerge for the first time, it's maybe going to be 1 or 2 weeks later, it's going to be in the north of England or Scotland. We don't account for this in the way we model, and we produce abundance trends at the moment. We've only got this single emergence time for across the whole of the UK. And we want to know, if we take this into account, will this change the abundance trends that we get out and make them a bit more robust? And it can also help in terms of the way we can analyze the data at varying spatial scales. So we've got this overall UK level trend. We also produce trends based on the 4 nations of the UK, but we want to know if we can get this down to finer scales. So maybe butterflies emerging are doing well, in the south of England, but doing poorly in the north of England, and this could sort of average itself out, and we couldn't see these trends. So we're going to take that into account by using these 32. These are branches of Butterfly Conservation, the charity in the UK, and it's basically, they do volunteering work at each of these branches. So it'd be quite nice for them to know at this spatial scale what's happening to species in their area. Obviously, the problem with this is you've got fewer data in each of these, and there's probably going to be limitations in terms of which branches can be used, how long they can determine the trends for, etc. So this is the model that we're going to be using. So it's a generalized abundance index. It uses concentrated likelihood, and this is just to decrease the computing time. And we find we can either fit it with a Poisson, zero inflated Poisson, or negative binomial based on the data for that species. And each species is entered separately into this model. Beforehand, each year was also entered separately, but we've developed a multi-year model just by combining the likelihoods over years. And yeah, this allows us to determine trends and parameters over time and share parameters amongst years as well. And in terms of seasonal variation, we can do a stopover model, a spline, or a mixture of normal to PDFs or a single normal if it's a single brooded species, which is what we're going to be using. So yeah, out of the normal distribution, you've got this peak, mu, and this is going to be the emergence time. So it's the peak emergence of that species of butterfly in the UK. So we're going to allow it to vary. So it's just a simple linear regression, basically. And it's going to be latitude, longitude, and the interaction. And the first scenario, basically, that we're going to use here is where we allow it to stochastically vary year by year, which is basically what we're doing at the moment. And the second option is then to allow it to have this trend over time. And so some results. So this is the UK, and we can see from this is the first scenario that there's more green later in the years, which is when they're emerging earlier overall, but obviously it's going to vary. And we've got the spatial variation across the UK as well. And then this sometimes works. This is supposed to move, but sometimes it just doesn't bother. This case, it's not bothering. So I'm just going to move my arms a bit to show what's going to happen. So it basically moves up the country and becomes more green with time goes on. It's sort of nice and yeah. So if you believe that, that's good. That is what's happening. But yeah, okay. Now we've basically determined what's happening with mu. But now we're going to see what happens if we add this into the abundance trend. So what we get when we use the GAI is the superpopulation size abundance. So it's the total number of individuals that we've estimated for a certain site in a certain year. And yeah, we're going to use that in just adding it to an extra GLM stage, plus this is the year and site effects. And then there's weighting in terms of sampling effort as well. We just take the year effect and put it on this log scale, and this is what we get. So this is the abundance over time from 1984 to 2018. And overall, you can see it's quite flat. So if you put a further linear regression on that basically go through the points and be pretty flat. Then what happens if we account for phenology? So this is without anything. Okay, the first scenario. So there's that one, latitude, longitude, and there's a red line there. It's very close to that black line, which was the original one, but there is an extra red one. So obviously it's not doing much. Then if we have this further limitation, so it's adding this time trend on, you can see it changes a bit. So this is a further red line compared to what without any phenology accounted for. But in terms of the trend, it's still quite flat. So that's, this is out of all the species that we tried, and we can try most of them. This is probably the most it's varied, all of them. So in a way, that's good. That's reassuring that what we're doing at the moment is producing abundance trends that are quite robust. But then in terms of varying the spatial scale, so this is the nations of the UK. So what we do is we have this overall model, and we allow it to vary, and then we take the superpopulation size and basically just subset it based on the region or the branch level, and then just do this GLM stage a bit further. So this is what we get. In there's the 3 different scenarios that we had before, but they're all, again, pretty close together. Out of interest, this species is just flat in England, but increasing in abundance in Scotland and Wales, which is nice. And then in terms of the branch level, that's exactly the same idea and how we do that. So this is just free region, so it's basically at the county level, but a bit bigger scale. And yeah, again, it's pretty similar. But we can see these are all in the south of the UK, and there's not a coincidence for that, because it's we've got a lot more sites that are being sampled there. I think if you go further up in the country where there's sort of black spots and sort of where you don't get much sites being analysed, then it's going to be harder to get this, because I think we need about 5 sites per year, I think, at least where we've seen this butterfly in it. So it's going to determine, it's going to be the more common butterflies, it's going to be the ones further south that we can analyse at the moment. But yeah, that's what we're getting. So yeah, in conclusion, we can see that our model can pick up these changes, latitude, longitude, and we can do this multi-year model to do these trends over time. But yeah, there's not really much showing at the moment. There's no large changes in abundance trends, so yeah, that's fun. So yeah, we're going to see if we can adapt this to species with multiple broods, and maybe something might happen with some species at some point. But yeah, that's thanks, and I think that's it.
Thanks very much. Is there any question?
Thank you for the talk. Did I get that right? The multi-volume case would also be possible to model with the GIA you used?
Yeah.
You just didn't apply it yet?
No, we used the simpler cases for it, and yeah, we've shown it for the species that change volcanism and things like that, and it's been shown and it can be used. But yeah, we just need to change it slightly, but yeah, it still works.
So we have time for a couple of other questions.
Thank you, and for your dance and your talk.
Thank you.
I'm curious about, like, there's lots of peaks and valleys annually. What's driving those?
Yeah, it's usually short-term weather conditions. So maybe if you've got a bad spring, they'll emerge a bit later. So this year in particular, I haven't been, maybe the last couple of weeks in the UK, we haven't seen much until, yeah, about 2 weeks ago. But the year before, it was really good spring. Loads of things were coming out at that time. And maybe just one, period of bad weather in the middle of the usual flight season, or just when they're going to start, and they delay it. But yeah, overall, the pattern is that they're getting them earlier over time, but it's just stochastics are change.
Yeah, okay, thanks.
Right.
Maybe another question?
I may have missed this, but what's the timing of your surveys? Do you do them at the same time, or are you trying to catch them when they're?
No, it's basically just transect walks where people sort of go through. It's usually protected areas that they do, and they just go. It's between about 45 minutes to maybe an hour that they do, and that changes based on site and like how long it takes to get through the site and get to the interesting bits in your site and things like that. But yeah, just as you walk along the way, you count butterflies either ahead of you, sort of in a 5x5 box as you walk along. And if a butterfly flies into that area, then you just count it, and that's it. Yeah.
Yeah, and is that like the same time of within a year, across years? Do you do that like the same weeks, or do you wait until flowers? I don't study butterflies.
Yeah. So yeah, it counts all butterflies throughout the season. So the main season in the UK starts in April, so it's beginning to get earlier, and it ends just basically at the end of September is when you see most of them. So they do it once a week for that. But yeah, it's the first day where the conditions are right to do it, because if it's raining, there's no point. So yeah, it does vary basically. And there's some weeks it could be horrible the whole week, and then you can't do a count at all. But yeah.
Okay, thank you.
Right.
Cool.
Thank you again for a great talk.
Thank you.
Now we are moving to our next speaker, Simon English, who is going to talk about quantifying phenology and migratory behaviors of hummingbirds using single-site dynamics and mark detection analysis.
Good.
Thank you. Yeah. This project that I'm presenting is work that I conducted at the University of California, Davis, with a number of collaborators, including my current thesis supervisor, Dr. Scott Wilson, at the University of British Columbia. So we learned a good deal about the background of migratory behaviors this morning, but briefly, animals employ diverse phenological movement behaviors And birds in particular use a spectrum of these seasonal movement strategies, where strategies may vary among species, populations, and individuals. And when strategies vary among populations, we call this partial migration, and facultative migration refers to the adaptive use of alternative migratory strategies throughout the life cycle of individuals. The costs and benefits associated with these diverse strategies differ, but for instance, we understand that migratory individuals are vulnerable to the effects of climate change, while stationary individuals are highly vulnerable to the effects of harsh weather conditions and resource scarcity. And so there is inherent value in studying these phenological behaviors for ecology, but there are challenges associated with this study, particularly in cohabitating populations of migratory and stationary individuals, where we get partially observed state information when we're marking individuals on the breeding phase. Furthermore, if individuals have the potential to transition among states from one year to the next, this further complicates the study of phenology in these dynamic systems. So the objectives of this study were to quantify the population composition of migrants and residents in a partial migrant system of hummingbirds. We aim to quantify probabilities of behavioral plasticity, so that facultative migratory behavior, and also quantify rates of apparent survival that are associated with each of these states. To address these aims, we studied 2 sites in California, USA, where at each of these sites, radio frequency identification readers were collecting data continuously over 3 annual cycles. And they were collecting data from over 1,000 hummingbirds that were tagged with RFID tags. You can see these very small RFID tags that are necessarily small for tracking hummingbirds. And we were studying these 3 species because we hypothesized that there were facultative migrants joined in with partial migrants and obligate migrants in this system. I think this video is not going to work, which is, maybe it will, maybe it won't. Unfortunate, but this is the data collection process that you can see where individuals are entering this reader station through the detector, drinking nectar from, or artificial nectar from these feeders, and then the tagged individuals are logged. And once we collect this data, it's retrieved continuously over the year. Once we retrieve this data, we're able to apply a multi-state model that estimates 8 probability parameters. The developers of this model are credited below here. The probability parameters that are estimated: apparent survival, there's an imperfect detection parameter, a parameter for state transitions, so transitions among the migratory states, important for studying this facultative migratory behavior. A persistence parameter, so that's related to the open, robust design framework of this model, which I'll elaborate on in the next slide. But this is persistence from 1 month to the next in this case. Similarly, the entry period refers to probabilities of entering the population from between monthly periods. Proportional state composition, so proportions in the population belonging to the migratory and the resident classes. Then some nuisance parameters for correct classification, and the probability of being in a given state in a given year. With these probability parameters, we were further able to estimate phenological parameters, including arrival time, departure time, residency, superpopulation size. We were not able to estimate superpopulation size, although it is a component of this model. That's because the redetection process is distinct from the tagging process. And finally, intensity of availability throughout the annual period. So once we've collected all this data, we apply this multi-state model. As I said, it's continuously monitored. The population is continuously monitored throughout monthly and annual periods. And individuals are probabilistically assigned to states. So that's the multi-state component with state uncertainty. And when we combine these features of the model, we get the multi-state open, robust design model with state uncertainty, kind of a mouthful, where survival is estimated over annual periods. Persistence is estimated over monthly periods when the population is assumed closed. And probabilities of entry are estimated also over these monthly periods. So we quantified the composition of this partial migrant system where migrants are shown in gray here. I think that's probably hard to see. And residents are shown in black from two populations distinguished by the symbols here. We found that hummingbirds adopt different migratory strategies within the same population. And importantly, all obligate migrants were correctly classified in our model, which is a good sign. Happy to see that. And then we also quantified plasticity and seasonal movement behaviors. So this facultative migratory behavior that we were interested in, where Anna's hummingbirds here at the, are the only species that were present in both populations. So they're represented by the circles and triangles here. We found that probabilities of becoming a resident were not different to probabilities of becoming a migrant. And probabilities of switching strategies appeared to differ among species, but not among sites. We found dramatically lower migrant apparent survival, which we partially attribute to a higher propensity for permanent emigration among the migrant class. So these survival rates down here are likely artificially deflated. We found differences between sites and we infer this suggests differences in site quality. Finally, we use this information to evaluate phenology, where migrants are shown to overwinter elsewhere in this population, which is as we would expect, and the resident class, which also includes wintering residents as well as permanent residents, reach maximum availability at the end of the year, annual period. So overall, we present a remote sensing framework for quantifying phenology in these dynamic systems. We applied quantitative methods to study migratory plasticity, and we observed distinct survival and emigration rates between residents and migrants, and this informs us about migratory dynamics, which is useful for our study of ecology. I'd like to thank my co-authors, my numerous co-authors, and the various other contributors and supporters of this project. But if you'd like to read more on this, it's published in the Royal Society Journal. It's in open access. You can retrieve the R scripts and data to replicate these analyses on Dryad. You can contact Dr. Lisa Tell, who is the corresponding author on this paper, or myself for further inquiries. And of course, if there is time, I'm happy to take any questions.
Thank you very much. Is there any question?
Hi, Simon. Awesome talk. I am kind of curious. You talked a little bit about how you thought your survival estimates were influenced by immigration and therefore like were inflated quite low. Do you have a sense of what you think? I don't know, just talking a little bit more about survival output from all the other parameters that you're able to estimate and their influence on that.
Yes, so I think I understand your question. Stop me if I...
Great, that makes one of us.
But survival estimates are expected to be biased low by high rates of permanent immigration, right? So the rates that we see in this study are very low, so low that you would, that's such a strong fitness pressure that migration would likely not evolve in this population if it were truly, if survival were truly that low, right? So we expect that that more likely represents either just a higher propensity for permanent immigration. Does that get at your question at all?
Yeah, I think I'm probably looking for like, what do you think survival should be? But, and we can talk more about that later.
Yeah, well, actually on that point, the resident class, the survival estimates of the resident class correspond very closely with other published estimates of survival for hummingbirds, even in this population. So for what they should be, the resident class is a good reference for that.
Yeah, cool. We can talk earlier. Thanks.
There is a question. So I was wondering if there is any signal for difference in survival between the individuals that switch strategy and the ones that keep the same strategy.
We weren't able to evaluate that. You know, these models are quite, I guess the word is data hungry, you know, but I think that's there's an opportunity to follow up on that in the future once we let these RFID readers collect more data, build a even more sophisticated model.
Thank you very much, Margarito.
So now it's time to move to our
Hi, everyone.
next speaker, who's Euring2023, who's talking about how to work the bee work, modeling bumblebee citizen science data.
Hi, everyone. Thanks for tuning in. My name is Euring2023. I'm a final year PhD student at the University of Kent, and today I'll be talking about modeling bumblebee citizen science data. This is joint work with Eleni Matuchu and Richard Kamen. So bumblebee are quite important as they provide pollination services and they function as an indicator species for change in climate or land use. Therefore, distribution and disruption in either the distribution or the abundance are thus a major concern from an agricultural and economic viewpoint as well as a conservation viewpoint. So bumblebees can be classified into four castes. Oil queens, which emerge from hibernation in early spring and establish nests. Workers that emerge throughout spring and summer and help to support the nests. New queens and males that emerge towards the end of the season and mate. Then new queens go into hibernation and some of them emerge the following year as new queens and the cycle starts again. However, number of bumblebees are known to be declining in the UK, and so the Bee Walk was established to monitor the abundance of bumblebees in the UK. Here, volunteers walk a monthly transect from March to October, and they record the number of bumblebees, their caste, and the species they detect. So bumblebee, the story so far is that it started from 2008 and it's still presently running up to 2023. And as you can see, the sites that were surveyed have increased and also the bumblebees. So the survey is getting better. However, not all sites are visited each month and visits can be made on any one day of the month. And then the cast can be identified as queens, workers, males, and unknowns. This is because new and old queens are indistinguishable, as they only can be identified as queens. Where any cast that wasn't correct, wasn't sure, because group 2, the unidentified group. So the issues with the data is that, yeah, we would like for it to build at a site and day level. However, the data is incredibly sparse, and this won't do. To counter this, we temporarily we group records to weeks and spatially to the NOTS1 region of the UK, including Northern Ireland, as this area wasn't part of the BWOC. So our model, we model the emergence, survival, and reproduction, and we also model the observation process, the identification. This model is based on the Matuchu et al. 2018 classical model, but we extend this model to allow for spatial temporal modeling in a Bayesian framework. This framework accounts for cast-specific and area-specific emergence with productivity and cast-specific identification probability. It also has a stochastic separation of queens to new queens and old queens, and that of unknown to all casts. To model the emergence pattern, we use a normal probability density function with area and cast-specific mean mu and cast-specific variance sigma, such that the entry probability beta at time between t minus 1 and t at year y, cast C at area S is essentially the difference of the CDF at t and t minus 1. Yeah, and then we have some checks to ensure that the sum of the entry probability is equal to 1. We treat the force and last as open-ended as such. So then we denote E as the number of individuals emerging from the cast in each area in each year between T and T minus 1. So yeah, all queens can then emerge. Emergence depends on the number of all queens that survive with probability epsilon and its entry probability. For the other cast, the number of emergence depends on the number of all queens, its productivity rho, and then its entry probability. So to model the spatial and temporal correlation among years and areas, we use a space-time separatable model where for the emergence and productivity, where SP is the spatial component, and we assign an ICAR spatial model to this. For the temporal component, we use a random walk 1 model. So this space-time model improves the strength of the estimation, allows us to produce nice maps, and yeah, allows good inference. So then individuals can then survive with probability phi, depending on the m individuals that are around. And individuals that are around is basically individuals that have survived and those that have emerged. Having m individuals around, individuals can then be identified with probability psi. And as you can see, we have cast-specific probabilities, identification probabilities. So then the number of individuals assigned to each group G, kappa, is basically for queens, is the old queens and the new queens. For workers, it's males, it's those identified as workers and males, and it's just the difference for those that weren't unidentified. And then finally, we model the aggregate of counts in area S, year Y, time T for each group as a Poisson with mean lambda, where lambda is proportional to the number of individuals assigned to each group, multiplied by the total number of sites visited in that area and time and year. So we apply this model to one species of bumblebee, Pasquarum, and we produce an emergence map for the forecast shown here. So you can see this paints a nice picture, as you can see the spatial difference of the emergent times of the different casts. We can also produce productivity maps, where productivity can be seen as a measure of population health. And so this can help us to see areas that are doing well and areas that aren't doing that well. Our model also gives estimates of caste-specific survival. So you can see how well a particular caste is doing. And then it also gives the identification probability to provide some insights on the observation process. So all in all, we've presented a dynamic Bayesian mixture model for the BWalk citizen science, and this model accounts for sparsity and enables spatial temporal modeling. This framework provides valuable information on caste-specific and area-specific demographic parameters such as genealogy and relative abundance, amongst others. Thank you for your time. Any questions and comments? Thank you.
Hi, Fabian.
Hi, can you hear me?
Yeah, I can hear you. Thanks very much for your talk. Is there any question among the attendees? Yes, there is one question there.
Hello, thank you. Is it working? Yeah. Thank you very much for the interesting talk. I had a question regarding how people identify the different castes and what are the chances of misidentifying the different castes. I mean, for my personal experience, a bumblebee is a bumblebee, so I don't know how to differentiate them.
Yeah, so normally people walk along these transects, and yeah, the identification isn't that great. Yeah, I can't remember, but our model gives estimate on the identification of queens, workers, males, and the identification bit as well. So yeah, I can't remember that well, but yeah, the identification of yeah, the caste isn't that great, and the identification probability is somewhat high depending on the species.
Thank you. Is there any other question? So if there is no other question, we are going to move to our next talk. And thank you very much again, Fabian, for a great talk.
Thank you.
So our next speaker is Euring2023. And so she's going to talk about distinguishing the biological process from the observation process in a tagging recapture experiment to study migration phenology of the Atlantic Salmon.
Yes, thank you. So, hi everyone, my name is Euring2023. I'm a PhD student and I'm working with Mathieu Bureau and Etienne Prévost on the migration phenology of the Atlantic salmon. So what is migration phenology? So migration phenology is the time at which an individual onsets its migration from an habitat to another. So the migration can be a very hazardous stage for some species. So the migration phenology is determined by both internal and external factors, which help to synchronize the migration with favorable survival and growth conditions. So this synchronization helps to reduce the migration cost. But we are in a context of climate change, and climate change can impact some of this factor. So it can have impact on the migration phenology and on the survival and the growth of the individuals. So the Atlantic salmon has a complex life cycle with different steps where the phenology can be important, and two migrations. So in my thesis, I'm working on the first migration, so from the freshwater to the ocean. So the juveniles undertake the smoltification, which is a bunch of change which allows them to survive in ocean water, and they migrate from the freshwater to the ocean. So my question is how the individual variation on the environmental factors it can influence the phenology of migration. But to know this, what I have to do first is to disentangle the observation process from the biological process. And this is what I am going to explain you today. So I'm working with data from tagging recapture since 2005 in the Scorff River in Brittany, in France. So during September, there are electric fishing, and the juveniles, the poor, are tagged with a pit tag. And some data are collected. And then some of these juveniles smoltify and migrate during the spring, and some of them are captured in two traps near the estuary, so the Prince Mill and the Leslie Mills. So, and some the salmon which are not tagged yet are tagged at the Leslie. And again, some data are collected, such as weight, length, and date of migration. And the goal is to use this capture-recapture data to model the biological process, which is smoltification and migration. But we have also to take into account the observation process, because we don't capture all the smolt that migrate, it's a partial observation. And the environment can have an impact on this observation process. For example, the discharge can have an impact on this observation process, but it can also have an impact on the biological process. This is why I have to disentangle the effect of the environment on both on the observation from the effect on the biological process. So I will show you how how we model the observation process. So we have two traps, the Leslie and the Mills trap, and we have some smolt that migrate. So for the observation process, we use the smolt that are not tagged yet. So they are untagged. And so some of them will be captured at the first trap, the Leslie trap, with a probability. There we are. And they are marked with a pit tag. And then, so among these, some of them will be captured at the mill, at the Prince Mill, and some will never be captured. Same for them, some will be captured at the Mill Prince and the Prince Mill, and some won't be captured. So we know the number of smolt marked at the Leslie, and we know the number of marked smolt at the Prince Mill. So this tag smolt allows us to estimate this capture probability. But what we have also to take into account, is the migration probability, because when the smolt is tagged, maybe it can migrate just after the tagging, but it can also migrate 2 days after, 3 days after, it depends. So if we don't see a smolt one day, maybe it's because it was uncaptured, or maybe it's because it hasn't migrated yet. So we also have to take into account this migration probability. Okay, so I hope you are not too lost, because it was the easy part, because now we have the environment. Yes, the discharge have an impact on the trap efficiency on both of them. And the discharge can also have an impact on the migration probability. And temperature can also have an impact on the migration probability. So we have to take all of this into account. And for now, we are working on this part, so between the Leslie trap and the Prince Mill. And we are trying different distribution, different effect of the discharge on trap efficiency, on migration probability, and also of temperature. And so here's some preliminary results for 216 and 222. So for now, the best model use the effect of the discharge on both the migration process and the capture process. Also the effect of the temperature on the migration process. And here what we were expecting for, so that the discharge and the temperature increase the speed of the migration, and that the discharge decrease the trap efficiency. Here are results for 216, which is not really what we were expecting for. And the result for 222, which is more what we were expecting for. So yeah, we have different results for different years. And so an hypothesis is because we have different data. For example, the discharge was lower in 222. And maybe also it can be an effect of the tagging, because here you have the recapture per day at the Prince Mill in 216. In blue, it's the unmarked smolt, and in red is the marked smolt. So here you can see there is a lot of fish captured, both marked and unmarked. And the day after, there is not a lot of unmarked fish, but still a lot of marked fish. So maybe these fish were delayed by the tagging. So maybe here there is a marking effect. But there is still a misfit with these models. So we're still trying to improve on the models and find a better way to model all this process. And after we will have the Leslie part, and then complete the biological process to then be able to forget about the observation process, because the truly interesting question is how the environmental impact the phenology of migration of the salmon, and how climate change can impact this phenology. So thank you for your attention, and if you have some questions.
Thanks very much. We have time for a couple of questions.
Can you model the fork length of the par as a covariate and also look at the growth rates of the fish that are recaptured?
Yes, we have the data for this, and so maybe we will do it when we will finish the observation part. Yeah, it's one of the goals to see how the growth during the winter can influence the migration, the phenology migration.
Any other question? I think there is a question here. So I have one. I'm curious. So does this modification always happen in the first year, or can it be delayed?
No, it can be delayed in the second year, for example. Yeah. Most of the time in France, it's in the first year. Sometimes it's the second year, and sometimes after, but it's very rare in France. But in Norway, it can be after, for example.
Does it happen that some individual never migrate?
I think some, but there is the sneaker, for example, the males that mature before migrating.
Okay, so they can breed before migrating.
Some male, yeah, do. Okay.
Thank you very much for a great talk. So our next speaker is Paul Cuchot, who is going to talk about habitat dependency of phenological sensitivity to temperature.
Hi everyone. So today I'll talk about some work we did during my first year PhD. So I start with this figure. So as you may know, the Earth is warming, and the increase in temperature is getting faster from the middle of the 20th century. And in parallel, in many species, we observe advancement in their phenology. So here for a species of swallow, and here in blue teeth, we can see that from the 70s, they started to advance their breeding. So the remaining question here is that are birds advancing their phenology because of the Earth warming? And so some researchers recently tried to answer this question, and what they showed is that yes, most of the temporal advancement is explained by warming. So it's especially the case for some passerine species like gray tits and blue tits, the one I'm going to talk about today. So their phenological advancement is explained between 70 to 80% by warming. And so most of the time, the reaction, the breeding date according to temperature reaction is explained by a linear reaction norm with two parameters, so an intercept and slope. If you change the slope, then you don't change the reaction according to the temperature, but you change only the mean breeding phenology. And if you change the slope of this reaction, you change the phenological sensitivity, and that's what we are going to study in this presentation. And so recently, some researchers highlighted differences in phenological sensitivity in blue and gray tits across Europe. And so they showed that populations located in deciduous habitats were more sensitive to temperature in their breeding phenology than population located in mixed and evergreen forests. And so in our study, we wanted to look at if there was an effect of habitat anthropization of the degree of phenological sensitivity in birds. And so for this, we first need to integrate degree of anthropization as continuous variable in our study. So the ideal dataset for this would be a dataset with many populations, inhabiting many sites with different habitat characteristics. And that's why we were interested in using the French constant effort site ringing data. So it's a MISNet capture a protocol which started in France at the end of the 80s, but earlier in Europe. So quickly, per site, we need at least 3 years of sampling, 3 sessions per year. And each time we capture a bird, basically we just identify it, aged it, sexed it, and put a ring. And so here are the sites we used for our analysis. So as you can see, it's pretty well spread in France. We have more than 240 sites. And so now we have an ideal data set, but not that much actually, because we don't know how to study the phenology using this kind of data. So that was part of the modeling challenge here. So to model phenology with this kind of data, we were interested in studying the change in proportion of juvenile as a proxy for breeding phenology, sorry. And so as you can see, adults in blue and gray tits are easily distinguishable from the juveniles. So we can easily calculate or look at the proportion of juvenile among the captured individual. So it's just a ratio like that. And so as you can see, so here is the juvenile proportion during the breeding season in blue tits for this year. And so as you can see at the beginning of the breeding season, there's no juveniles, so the ratio is equal to 0. And as the breeding season progresses, we have an increase in proportion of juvenile until reaching an asymptote here. And so to study the phenology, we were interested in quantifying different moments of this curve. So we use the 3-parameter function. So the first one is the asymptote. So it's the asymptote at the end of the breeding season. The second parameter would be the scale parameter here, which is just a shape parameter. And the last one is the X-mid parameter. So it's the one we'll consider as a proxy for phenology. And so it's the day at the inflection point of the curve. So as we want to study the phenology, we'll extract this parameter and make it function of temperature to look at the sensitivity per species. But we can also integrate environmental factors this way, plus their interaction with temperature to see if this environment has an effect on the phenological sensitivity to temperature. We've did this kind of model using JAGS in R. And so going back to our problematic, we wanted to look at the effect of anthropization. So for this, we needed to quantify it. And so blue tits and gray tits are forest species, and they can be located in urban areas too. So we were interested. We finally decided to measure the tree density and the imperviousness around each capture site in a 1 kilometer buffer. And so here are the first results of the model. So here we don't take into account any environmental variable. But as you can see, so here in blue is the mean response to temperature anomaly, so for both species. And each gray line is the site-specific response to temperature anomaly. And so as you can see, yes, you can see, let's say, there is a difference in sensitivity between sites and between species too. And so now we can integrate our both environmental variable in the model and then look at their interaction effect with the temperature. And so as you can see, we have a significant negative effect of forest density and imperviousness on the phenological sensitivity in blue tits, but not in red tits. And so here are the projections of the model. And so the first result would be that the average phenology is earlier in urban areas for both species here. So most of the time it would be explained by the fact that urban areas are hotter than the other sites, but actually in our model we controlled for the mean temperature of the site. So we explain this earlier phenology in urban areas, maybe because of artificial light or food supplementations. So that was some arguments that we found in the literature. And the second main result would be that the variation in phenological sensitivity is explained by the environment only in blue tits and not in red tits. And so, as you can see, blue tits are more sensitive to temperature in sites with more important imperviousness degree. So that's something we can't really explain until now for this reaction, but we suggest that it could be explained by the difference in food diet between our two species. So the blue tits is known to be more specialist in its diet. And for perspective, so we did those analyses for two species that we already pretty well know, but we can extend this study to non-hole nesting species and then investigate how differences in ecological preferences can shape their breeding sensitivity. And that's all for me. Thank you.
Thanks very much. So we have time for 2 questions.
I wonder if you compared the asymptotes, how high the ratios got as maybe a measure of fecundity possibly being affected by climate change?
Sorry?
If you look at the very top when age ratios of juveniles to adults reach their maximum, that could be an index of fecundity. I wondered if you looked at whether that was also affected by earlier or later seasons.
The thing we did to look at that is that we just look at the correlations between the different parameters. So the X-mid parameter, which is the parameter for the shift in energy, and we looked at if there is a correlation between the asymptote and the shift in energy, and that was not the case. So in a way, we controlled for that. Yes.
Any other question?
Yes.
Thanks very much for a really interesting talk. Did you consider whether there might be variation in capture probabilities, either through the season or between age classes, that might affect your results in any way?
We looked at the effect of some environmental factors on the proportion of youngs. We didn't find any effect of the environment on the proportion of juveniles. I don't know how to say that. Does it answer the question or not?
Not completely. I was wondering whether you should more formally model the probability of capture. For example, in the adult birds, later in the season, you may get more birds molting, and that may affect their probability of being captured relative to juveniles.
Yeah, we could have, but we didn't.
Okay, thanks very much.
Thank you very much. Thanks for the attention. And so that's now the end of our session, and thanks to all the speakers. And there is a break, I guess, for 10 or 15 minutes. 10 minutes.
Yeah, because I'm also. So I think there is. Yeah, which.
I would have thought in an urban environment it would be the other way around, but I don't know.
The feeding chicks.
Yeah. Yes, of course. Yeah. So they'll get stuff.
They would actually scarce.
Yeah, that makes sense. Yeah.
Yeah. Hold on. Great work. Discussion at some point.
Basically, what
that's the assumption that everything and it's interesting. Just to say that we shouldn't look at so I think it's possible. But that's yeah, no, exactly. But I think this is also catching over a relatively short period. But then the apples do more. So it is possible. So you It's not strict category, it's in part. These, okay, so this is the reading trials and through the season. It's just a portion of yeah, so the everyone is the adults and so it's just front so it's possible, just which I understand. Yeah, the sort of mean number of captures. So this is these are sessions. So May, June, July, August. So these May. So it's in the period. So May, June, July. This is a lot. This is very different. This is very similar. Yeah, but you see for this because the adults are slightly more, so they are much less The timing. So for France, so it's yeah, I just yeah, so we capture not the others. That's the others. So you don't capture, we capture. So actually, within hours of capture, where we add more than we have as capture and then we'll pick
Ok. Cool, merci.
Yeah, I'll let you know if there is time enough for questions or no time. Just act like.
No power tonight. Okay, everyone, let's get started with the last talk session of the day, starting just after 4 o'clock. So I hope you're still with us. You should be, because we have birds, wolves, and kangaroos for you now. And let's get started with Euring. She's from here, from University of Montpellier, and she'll be talking to us about modeling the impact of canine distemper virus on the Yellowstone wolf population.
Thanks, Clay. So it's just my name here, but it's many people involved that will need to show their face, so they will appear afterwards in the talk. So I'm going to talk about wolves and disease, and many of us know dramatic impacts of disease on wildlife. For example, the 95% mortality risk of gorillas to Ebola, or the amphibian chytrid fungus, or sea stellar wasting syndromes, etc. So hopefully, facing such strong selection pressures due to disease, we might hope that resistance might evolve. And for that to happen, first, resistance need to emerge in the population, for example, via a mutation on an immunity gene, and then it needs to spread into the population in order to be transmitted to the next generation. And for that, being able to signal its resistance and so that it can be passed on to others can be very interesting. So in many vertebrate species, darker coloration is associated with higher exposure to pathogens, for example, through different behaviors, more bold individuals, and also to better resistance or worse resistance in some species. Okay, so there is a link in certain vertebrates between coloration and disease. And in other species, like many birds, coloration is also used as a cue for mate selection. So coloration, when resistance is genetically determined, it has the potential to be used as a mate cue and a signal for individual quality, and in certain cases, maybe to pathogens. So wolves have a striking color polymorphism, and it's due to one single mutation on a single gene, a 3 base pair deletion, and it turns a gray wolf into a black wolf. In Yellowstone, a genetic study has shown that there was a single event of introduction of this mutation into the population, and that was about 7,000 years ago. It was introduced at a very low frequency, so the black allele should have disappeared. But no, instead of that, it actually spread, and it's cited as one of the most rapid spread of an adapted variant known in vertebrates. And it can be found in many populations across North America, and in very high proportion in some populations. And genetic studies have shown that there is a selective sweep, so positive selection on this coloration gene. So our hypothesis was that maybe, and based on the literature, that maybe black coat is associated with enhanced immunity to a respiratory pathogen, because it encodes for a protein that is a beta defensin and that play a role in immunity, or maybe also through pleiotropic effects, so that it can act maybe on genes implicated in immunity. So we wanted to test this hypothesis in wolves. And for that, we could use the amazing data from the Yellowstone Wolf Project. So wolves have been extensively monitored since they were introduced in the 1995. We know many things about their demography, genetics, pedigree, behavior, morphology, exposure to disease, to different pathogens, etc. So canine distemper virus, that I would call CDV, has struck several outbreaks have struck in the park. There were 2 more than with 3 since this graph was published. And it's one of the most common pathogens in carnivores. It's responsible for the decline of many carnivore species. And in wolves, it's associated in Yellowstone with high mortality, especially among juveniles. There are many black wolves in Yellowstone. Black and gray wolves are in the same pack. So it was the perfect study system to explore this question. So we started with estimating vital rates of the wolves. For fertility, we use GLMLs. For survival rates, we use multi-event capture-recapture models with epidemiological states to test whether exposure to canine distemper virus would have an effect on survival. We considered body weight, pack size, population density, many factors, but I'll just present you the results for coloration and disease status. So on recruitment, that's a previous study from Dan Staller. He found that recruitment was divided, well, half of the pups in average die during canine distemper outbreaks, and independently of coat color. And black wolves, black females, always produce in average 25% less pups than gray females. Concerning survival, we found that black heterozygote and gray wolves in average had the same survival, except that when they were exposed to canine distemper virus, black wolves, black heterozygote have the same survival, but gray wolves have a decrease in about 23% survival. So there is a strong difference in survival rate when exposed to the disease. So this was interesting to us because it means that disease can modulate the survival reproduction trade-off, and that black heterozygote can have an advantage when exposed to the virus, but is it enough to compensate for the reduced fertility of black females? I didn't show you the results, but black homozygote have a very low fitness. They reproduce badly, they survive, they have a low survival, and that's why it's very few of them in the population, about 5%. So we wanted to explore whether the general fitness, how is the general fitness of the wolves with different genotypes. And for that, we built a population projection model. So that's a very shitty representation, but I did my best. So basically, it's a 2-sex model. It's also structured by genotype, and it's aimed at representing the main life events in the year of a wolf. So a wolf has a certain survival probability depending on its genotype and sex. Among the survivors, we can select the breeders, and then the breeders select their partner to mate with and transmit their genotype. So we know that coat color is a Mendelian inheritance process in Yellowstone, and recruitment function determine how many offspring of a given pair will survive into the population. And we can project the population, track population growth rate, genotype and phenotype frequencies, and also look at what is the optimal mate choice strategy in this population. Is it to mate randomly with an available wolf, to mate with a wolf of the same color, or preferentially with a wolf of a different color? So we checked that the model, even if it was quite simple, reflected roughly what we observed in Yellowstone, and it was pretty good. So here I'm just showing you the expected frequency of black wolves. Gray line is the observation until here, and the 3 different color lines are the model predictions with different mate choice strategies. So what we see is roughly we end up predicting 55–60% of black wolves in the park, except if the wolf were mating preferentially with a wolf of the same color, then we would expect a lower frequency of black wolf in the park. So this is not really likely to be happening. Then we can play with this model and vary the frequency of outbreaks in the population. So here on the x-axis, and look at the frequency of black wolf oh wow, caught in the population. So we see that if the outbreak frequency increase, we expect more black wolves in the population, except under associative mating, we should expect the black allele to be wiped out from the population. We can ask what's the optimal mature strategy, and this was really cool that about one outbreak every 10 years, the best is to mate with a wolf of a different color for gray wolves and also for black wolves in order to produce heterozygote offspring that would be resistant to the disease. It means that disease can select for the evolution of matures, and it's actually what we observe in Yellowstone, which was really cool. So genetic evidence, and also when we look at the pair association between wolves, we see an excess of black-gray pairs. Well, we found that very cool, but the reviewer said, well, it's just one model, it's just a single population, so it's not enough. So we're like, okay, let's look across populations. So my colleagues have collected data on 12 populations across North America. Here is showing the frequency of black wolves, and we find that it was positively associated with CDV prevalence in the populations, and that the probability of a wolf being black was higher among wolves exposed to CDV, which is in support of their higher survival when they're infected by disease. So it's in support, it's all pointing towards the fact that the black coat color could be an adaptation to disease, and it could be maintained in population via the evolution of mate choice. But this hasn't been confirmed experimentally, so we don't know through which mechanism it could work. So it's still a hypothesis, let's say. And of course, other things probably play a role, other pathogens, other factors to explain the frequency of black wolves observed in North America. Yeah, I said the rest. Maybe I can just say that this study was quite interesting to show the interest of mixing, I would say, demographers with wolf biologists, geneticists, and epidemiologists. And with that, I'd like to, oh shit, thank you. Sorry, why isn't it appearing? Oh. There is your face, Molly, to thank my collaborators, but I don't know why the last slide won't show up, and it's nice pictures. Oh, and one of the wolf people is in the room, so I think it's very cool. Thank you.
Hey. Time for 2 questions for Sarah. Yes, we have a question up there.
Hi, it was very nice. Maybe it's a very naive question, but I would always think like the fur color would be like will act on maybe the success of hunting. And if they're darker, maybe they have less success in the hunt. Did you look at that, or?
So that was a previous hypothesis for explaining why there were more black wolves in certain populations than others. First, they thought, oh, in forested areas, maybe being black is not a disadvantage because the prey cannot see you. But first, the wolves are cursorial predators, so their prey clearly see them and they don't care. They still run after them. And but the main thing is that the 2 black genotype, they have very different fitness. So they have the same black color, but the black heterozygote has a high fitness, especially in presence of frequent disease outbreaks. And the black homozygote, who has the same phenotype, has a very low fitness. So it seems that and also the genetic evidence really showed that there is positive selection on the gene for coat color. So it seems that it's not a phenotype thing, at least not just a phenotype thing, but there is some genetic mechanism happening. But yeah, maybe I was thinking about that maybe at some point, black wolves were more hunted for the fur or things like that. So we were trying to look at the price of the fur in the old times. But yeah, we should. Yeah.
Another question?
So the Yellowstone population's in a protected area, but when you looked at other population of wolves, were those hunted by humans currently? And if so, would that affect the results you saw?
Sorry, I didn't get the last part.
So the other populations of wolves that you looked at, to just a reviewer's comment, were those in hunted populations by humans or not? And if so, would that result change the result, do you think? If there was human
The fact that they're
pressure?
hunted?
Yes.
Yeah, exactly. So that's what I was just saying before. So we were wondering maybe they would hunt preferentially darker or gray wolf, but we don't have any evidence of that at least. And the distribution of the coat color that we observe in all these populations, they're probably also the results of very long-term selective processes. But I mean, wolves have been so heavily hunted that it's probable that humans have played a role in selected certain phenotypes. But that's what I was saying just before, that the two black morphs, they have very different fitness, even if they have the same black phenotype. So at least there is at least something else at play. Yeah.
All right. I'm afraid we have to move on. Perhaps Sarah had the next opportunity and ask all the other burning questions. Our next presenter is joining us online. It's Anna Payo from the School of Biological Sciences in Aberdeen. And she'll be talking about long-lasting effects of harsh early life conditions on adult survival of a long-lived vertebrate.
Hi there, my name is Payo, and I'm going to be presenting this talk on behalf of Ana Sanz Aguilar and Dani Oro, who have also been working with me in article. So the question that we were interested in was to understand whether harsh environmental conditions experienced during early life had a long-term influence in population dynamics. And we are not the first to ask this question. It's long known that the individual fitness is the result of a complex interplay between the individual's genetic architecture, the environment they experience through life. However, understanding how environmental conditions at different life stages in life history traits can facilitate the prediction of population responses to environmental change. And the conditions experienced during early life can be an important source of individual heterogeneity. There have been different non-exclusive hypotheses that are aiming to explain this kind of heterogeneity. For instance, the first one is the classical silver spoon hypothesis, which states that those individuals that are born under good environmental conditions will generally outperform those born under harsh environmental conditions. Then we have the viability selection hypothesis that predicts that harsh environmental conditions can act as mortality selection filters, removing frail individuals from the population, and that survivors will experience increased fitness later in life. The third hypothesis, the predicted adaptive response hypothesis, that states that individuals experiencing similar conditions during early life and late life will experience increased fitness. And essentially what we want to do is to see whether any of these or some of these hypotheses hold with our data set. And to do that, we benefit from a long-term monitoring system of the Euring gulls breeding in the Western Mediterranean. And they are a very good study species, the Euring gulls, because we have already evidence that there are two early life selection filters that affect the juvenile survival of the species. Specifically, cohorts of Euring gulls experiencing low density dependence and benign winter conditions showed significantly higher survival in our previous study that we published in the Proceedings of the Royal Society in 2016. And what we want to do now is account for a larger scale that allows us to account for dispersal and see whether we can assess these three hypotheses in a more robust way, because before we failed to identify those long-term effects, but we think it's because we were missing dispersal. And at the same time that we do this, we want to know how does age and experience might be modulating those responses. So basically what we did is that we built a multi-event model that is able to account for uncertainty in some of the underlying states of the individuals. I show you here the formulation, but don't worry if you don't understand anything. It's just for the people that might be interested in the model. But basically what we do is that we build a capture-recapture model that accounts for density dependence and winter conditions both during early life and also in the current time step, while accounting also for age and experience and dispersal. And then we use ANODEP to estimate the proportion of the variance that each one of those variables has explained. So what you're seeing here is are three graphs that basically represent the same thing. So these two graphs are just sections of this graph at high levels of the two covariates. So we have here the winter conditions, and here we have the density dependence. And what we see here is that both early life conditions, the food availability, and the winter conditions have a negative effect on adult survival. And that means that those individuals from cohorts experiencing benign early life conditions had lower survival than those experiencing harsh conditions. Here I present the ANODEP table that shows the proportion of the variance that each one of these models explain. And what is more important here is that the combination of the early life conditions, so the effect of the first winter condition and the density dependent effect in the first winter condition, explain 54% of adult survival variance, and that is quite a lot. However, when we were assessing the conditions of the current conditions, those two covariates only explains 5% of the temporal variance. So our results support the viability selection hypothesis, with cohorts experiencing harsh environmental conditions during early life, both before fledgling and during the first winter, are subjected to immediate mortality filters to selective disappearance that cause improved survival during adulthood. Here we're seeing the same kind of graph that we were seeing before, but here it's broken down for inexperienced breeders, experienced breeders, and the three age classes. And basically, as life history theory predicts, that young individuals and inexperienced individuals would experience comparatively higher reproductive costs than those that are more experienced. And if you look here, these two age classes are those bears that are inexperienced and start breeding at 4, and these ones are inexperienced and start breeding at 5, and the survival significantly decrease through time. Finally, our qualitative exploration of predictive analysis responses showed that we had no support for survival resulting for differences in survival resulting from environmental matching, but this is again is a qualitative exploration. So overall, we saw that early life conditions explained a large proportion of the adult survival, up to 54%. However, adult cohorts experiencing poor early life conditions had higher survival in accordance with the viability selection hypothesis. Our results also show that apparent inexperienced breeders saw lower survival than experienced ones, and that adult survival decreased with age. These results could suggest an increased cost of reproduction for the fair breeders and individual quality differences or survival senescence in this population. Overall, our study highlights the importance of early development, age, and breeding experience as potential factors generating heterogeneity and survival between cohorts. Understanding the mechanisms driving the responses of early life conditions at different life stages is fundamental to understand the long-term dynamics of wild populations. Finally, huge thanks to my co-authors, colleagues, our funders, and I'll be around if you have any questions.
Okay, I can see that Anna is with us online. So do we have any questions for Anna? Well, while the audience thinks about it, I have a question. Anna, can you hear me?
Yes, can you hear me?
Yes, we can hear you too. Perfect. I was just wondering, like, so you found these like differences between cohorts. I was wondering if you've looked at all or have any ideas or thoughts on kind of within cohort variation. So some of the talks earlier today were all about variation between individuals. Do you have any idea how that looks in your population?
So we haven't looked at it specifically for this particular study. And I don't have any, I suspect that there is differences within each one of the cohorts. What I would be worried about is that for my liking, they're already pushing a little bit what we can do, because we are testing age, we are testing cohort, we are testing time. We are kind of like using all of these three factors that are already kind of like, if you cohort by time is age by time is cohort, and so on. And I think we are already in the framework that we're using. We're pushing a little bit what it can be done, and then trying to go a lower level within that. I would be a bit cautious about that. It's not that it doesn't exist, but I'm a bit uncomfortable about that. I don't know if I'm explaining myself.
Great, thank you. Another question from the audience? Yes, I have a question up there.
Hi, yeah, thanks for your talk. I was wondering if you saw differences in the individuals that experienced harsh early life conditions, if they had a different growth trajectory, just because I've read some papers where, if individuals don't grow very well early on, but then later on they have to grow really quickly, like it's called catch-up growth. To get at a certain size, there can be some costs associated with that, and that's often associated with lower survival. So I was wondering if there were differences in the growth for some of those cohorts.
Yeah, so one of the things that we would have also liked to look at is where there's differences in growth, and also how they do in terms of reproduction later on the success. But the kind of monitoring that we have for those colonies does not allow to do that. So that data is not available as that. So yeah, I don't know if there might be, but we haven't been able to test that.
Great, thanks so much, Anna.
Thank you.
We are sticking with the bird theme, but moving on to our next talk. So our next speaker is Camille Schatz. She's from the Centre d'études biologiques de Chizé, and we're focusing on intra and interspecific demographic variation into phylogenetically related seabirds. Take it away.
That's right, thank you. So hi everyone, so I just started my PhD at the Centre d'études biologiques de Chizé in last autumn with Karine Delors and Christophe Barbon. And so today, yes, I will talk to you about intra and interspecific demographic variation into phylogenetically related seabirds. So in the global changes context, it became important to understand how these changes will affect the population dynamics and of ecosystems. And at the population levels, populations are submitted to environmental variabilities, and understand how they will respond to this variability can help to understand how they might respond to the global changes. And one leading idea is the betaging strategy theory, so which addresses how individuals should optimize their fitness in variable environment. And this will say that in high unpredictable environment, individual will have higher survival rates in order to maximize the opportunity of reproductions, but at the cost of the current reproductions. So there, and it would be inverse in other conditions. And so according to these strategies, individuals should lower their fitness variability over time to maximize their long-term fitnesses. But even if this theory is well known, it remains relatively less shown in empirical studies, as we need population with similar ecologies that are living in different environments with different variability, and that we need enough data to study this over long term. So with this theory, we expected differences between the inter and intraspecific levels. So here we propose to study 2 species with 4 populations. So the species are the light-mantled sooty albatrosses and the sooty albatrosses that are 2 closely phylogenetically related species with different conservation status, as the light-mantled is near-threatened and the sooty is endangered. We have relatively few studies on their demography and on their local adaptations. And here we propose to make comparisons among the 2 species, 4 populations, 2 of each, on 3 different islands and so 2 climatic areas. So for the geographic part, they are in some French Auvergne territory. And so we can find the light-mantled in Crozet and Kerguelen, whereas the sooty albatrosses are found on Crozet and Amsterdam. And if we make some prediction about the environmental variability, if we expect it for the light-mantled, there will be more variability, more stochasticity in Kerguelen, as we found cats that are not on Crozet. And if we have a look for the sooty ones, in Amsterdam, it will be more stochastic, as there are cats and also avian correa that are not on Crozet. And if we want to compare both, one of the differences that we have is that the light-mantled are foraging in the south of Crozet, whereas the sooty albatrosses are foraging in the north of Crozet. So as there is more variability in the sea surface temperature in the last 30 years in the north of Crozet, we'll say that the sooty albatrosses environment is more stochastic than for the light-mantled. So we can expect this gradient of environmental variability on where you have here the light-mantled and here the sooty ones. So those are the data that we have. We have such long-term data, and you have the sooty ones, and you have at each time the number of individuals that we kept for the capture or capture data. Here, it's good to know that we only have adult ones there. In the data that we have to deal with breeders and non-breeders. For the breeders, we have information maybe of if they are successful or failed ones, if they failed at egg or chick stage, and we also have to deal with uncertainty. And they also are biennial breeders, so we have unobservable states. So for all of this, we made multi-event marker capture models. So I would like to thank Emmanuel Cam for our presentation of yesterday, which introduced a bit, but I will show you again a bit more. So here you have the observable states. So you have one individual can be a successful breeder, failed breeder, or non-breeder. And on the year after, if they don't come back at the colony, they will be in one of the unobservable states, and there will be a year. And if they don't come back, they stay in this stage until they come back at the colony. So our modeling was made on eSurge, and we also performed a goodness of fit test on UCare. And for all of the data sets we had, none of them was significant, so we used the model as it. So here are for the results. So we have the survival probability. So it's quite high because it's still albatrosses, but we see that there are some variability among the 4 populations. If we have a look at the probability of return to the colony, as we separate the successful breeder here is the ones that make 2 successive reproduction events, whereas the other not. So we see that for other ones, the return probability to the colony is really high, but not for the one that make two successive reproduction events. And if we just focus on those ones here, we see that there is variability among the different populations. And it seems that the probability of making 2 successive reproduction is decreasing with environmental variability, even if it does not really fit for the light mantled incrusé. If we have a look at the breeding probability, it's quite the same for the light mantled, but for the sooty albatrosses, it's decreasing with the environmental variability decrease. And if we then have a look at the probability of success, here we see that there is huge variability between the 4 populations, and it's decreasing the probability of success is decreasing with an increasing environmental variability. And so we made some comparisons among them. So we compared the survival with the breeding probability, and with the bait hedging strategy that I proposed you before, the predictions are that the survival will be higher with the lower breeding probability, and it seems that it's good, it fits quite well, but not for the sooty albatrosses of Crozet. If we have a look then at the survival and the breeding success, the same, if we keep in mind the prediction with the bait hedging strategies, it will look like that. And in fact, it quite look like that, but within each species, there is this phenomenon, but in the intraspecific levels. And if we then have a look at the survival and return probability of the ones that make 2 successive reproductions, we also have these trends with the bait hedging strategy still. And we see also that the survival rate is higher when they do not make 2 successive reproduction than others. If we also have a look at the growth rate, we see that for the light mantled, the population are stable or increasing, whereas for the sooty albatrosses, they are decreasing. And if we have a look at the growth rate and its variability, it seems to decrease with the environmental variability, even if it does not fit for the light mantled. And this is what was expected with the bait hedging strategies, as individuals will tend to have lower variabilities to face the environmental variability and to maximize the fitness at long term. So to conclude about that, some results are coherent with the predictions from the bait hedging theory. As we saw, there are some trade-off with survival and breeding probabilities, and also with survival probability of success, and also survival and probability of return to the colony for the successful breeders. They also have variability in the mean value of lambda that fits these predictions, but it does not fit at any time for all of the population. So there are still some that we have to explain. And so then we have to estimate temporal variability of parameter and compare between the population and parameters. And we will have to test for effects of environmental covariables, on demographic parameter, and we will study this on land, but also at sea. So we'll try to take into account the temperature, wind, precipitations, phytoplankton, sea surface temperatures, and also introduce predator and disease, where we expected huge differences depending on the district. So I would like to particularly thank the volunteers from the civic services involved in the long-term monitoring, and also Dominique Joubert for the data management, and you all for listening.
there any questions for Camille? Yeah, there we go.
Thank you for the presentation. Maybe you mentioned it and I missed it, but did you look at the covariation between survival and breeding success within populations, if you have a negative or positive correlation between these two types of parameters?
Between which, can you just repeat with it?
For example, between survival rate and breeding success within a population, if you have a negative trend or not?
That's just what I showed. You want the breeding success, that's right, and survival. That's right. Oh no, we made consent model for this, and we do not look further yet, but we will. It's just preliminary results there. We'll have more look.
Thanks for a really interesting talk. I was wondering, so you kind of ranked or classified them according to environmental variability in a really clever way. I was wondering if you also considered just the mean environment. Was that different?
What do you mean by the mean environment?
Well, so would they have differed in things other than the variability of the environment? Were they otherwise quite similar? Or was one of them experiencing just generally better conditions than the other, for example?
No, yet it was just, we did not take this into account yet. It was just to try at the beginning to classify that, but we still have to make it. We probably missed most of the other parameters that can impact the variability and just the total environment. But yes, we may have to do this.
All right. Thank you very much, Camille.
Sure.
Okay. That was kind of hard, the kangaroos. As promised. So let's welcome Rachel Bergeron. Yeah. From the University of Sherbrooke in Canada. Yeah, as promised, this will be about post-weaning survival in kangaroos.
Yes, so it's not too close, not too far. So just as she said, my name is Rachel. I'm a PhD candidate all the way from Canada. And I'm thrilled to be here to chew your ears off about kangaroo survival patterns. So quick shout out first to my incredible co-authors, Gabrielle Pigeon, Wendy King, and my co-supervisors, David Forsyth and Marco Festarian-Kent. Okay, so the population dynamics of large herbivores are typically influenced by complex interactions between density dependence and environmental variation, potentially via a common effect on resource availability. Nonetheless, the relative influences of density dependence and environmental variation remain difficult to assess, among other reasons because they do not act directly upon population growth rate, but via individual vital rates like survival, reproduction, emigration, and immigration, which then determine population growth rate. So populations of large herbivores are highly sex and age structured. So in our very well-studied ungulates, we will often find 3 age classes between which survival rates vary quite a bit. So we'll have a juvenile age class where survival is low and varies a lot from year to year. We'll have an adult or a prime-aged age class where survival is consistently high. And then again, a senescent age class where survival lowers and varies a lot again from year to year, as was found here with the chamois. So we typically end up with a survival pattern that looks something like this in a lot of large herbivores. So kangaroos are an interesting subject for the study of population dynamics, among other reasons, because kangaroo populations experience particularly large fluctuations in size compared to a lot of other large herbivores. So does this work? Yes. So patterns where this population here, for example, triples in size in 2 years and then again comes back down to 1/4 of its size in 3 more. This kind of thing isn't necessarily uncommon in kangaroo populations, which is useful for the kind of modeling we're trying to do. And kangaroo populations, a lot of them are also subjected to particularly erratic environmental conditions, which is why early studies have long focused on the influence of food supply and the effect of drought, typically using rainfall as a proxy. So some of them have come up with some relationships that were promising, looked something like this, where more rain meant more kangaroos or a greater population growth rate. But upon further digging, these studies have led to conflicting results and haven't generally held up. So potentially, however, some of these results might have been a result of changes in population age structure, which few to no studies have had the necessary data to account for yet. So the objectives of this study were to assess sex and age-specific survival probabilities, and then to see how food supply and population density influence these survival probabilities in a large herbivore, which inhabits a particularly variable environment. So the eastern gray kangaroo is a large, long-lived marsupial grazer. The study population inhabits 110 hectares of coastal grassland, which looks something like this, in Wilson's Promontory National Park in Victoria, Australia. Population has been monitored by capture mark recapture since 2008, which means we now have 15 years of data on just under 1,400 individuals. So the regular field season happens from August to November every year, at which point kangaroos are captured and they're marked with collars and ear tags and tiny ear tags on the tiny ones. And so that we can then return every year and follow survival long-term, of course. Age is determined a couple different ways, but for most of the kangaroos at this point, if they are caught for the first time as pouch young, then we know the cohort with absolute certainty. But for a lot of ones who are only ever caught as adults, if we can find them after they've died, assuming we can get our hands on the skull, we can estimate age at death based on the progression of molars. So the population density has been estimated 4 times a year by distance sampling, so once a season. And forage availability also estimated once a season every year based on a system of 30 to 50 some exclosures, like the one you see here on the right, which keep all herbivores rabbit-sized or larger out so that we can see what may grow. Right, so I'm sure, as I gather, a lot of you are familiar with the Cormac Jolly Zebra model, so I won't dive too much into it, but this is the model we use to estimate apparent survival in our population. So for those who aren't familiar with it, real quickly, it's an open population capture mark recapture model, which allows us to jointly estimate survival probabilities and re-encounter probabilities. So we fitted it as a state-space model in a Bayesian framework. Now, this model does make the assumption that all of your individuals within one group or age class have the same survival and re-encounter probabilities, hence the importance of carefully picking out biologically meaningful age classes. So we landed on these 5, so a couple more than the typical 3. So we would have a juvenile age class for the 0-year-olds, if you will, a subadult age class for 1 to 2, prime-aged age class for 3 to 6, and then what we called pre-senescent for 7 to 9, and a senescent age class for 10 and up. Now note that this looks like a big age class, but past 14, we have very few kangaroos in there. So this is a distribution of our sample size throughout the years for the study. So this shows, well, gives you a good idea of course, the sample size every year, but more interestingly, of the population age structure through time. So if we take a look at this blue age class here, this would be our prime-aged age class, the ones which theoretically would have the greatest survival and reproductive rates. You'll notice some years here, it represents about 9% of the whole population, whereas 2014, it's over 40% of the whole population. So we can imagine that if vital rates differ between these age classes, then age structure could play quite an important role in the population dynamics of this population. So we compared a dozen candidate models with different combinations of our environmental covariates, so population density and available forage, and a combination of both, so available forage per kangaroo. These were compared by Watanabe-Akaiki information criterion. And as you'll notice, these two are technically our best for females on the left and males on the right. However, then all of the models, at least for females here, were within 3.2 delta WASD every time. Within males, it's a bit more, but for most of them, still under 7. So we hereafter show results from the simplest age-dependent model. So these are our annual survival probabilities. If we were to take them one age class at a time and add the 95% credible intervals on there, our juvenile survival, as predicted, varies quite a bit from year to year, from essentially 0 to essentially 100. And then for our subadult age class, survival is already a lot higher and a lot more constant, though there's still some variability. until we get to the prime age class, where despite this enormous variation that we saw in environmental conditions, survival rates are very, very high every year. We're talking 94% and up every year for females, and always above 83 for males. You'll notice also there's a significant difference here between the two sexes, here and in this age class as well, where survival starts to lower again, starts to get more variable. And finally, our senescent age class, where survival rates are again quite low and highly variable. So I put this image back up again, so we can, now that we know survival varies quite a bit between these age classes, we can imagine that, say, our 2018 and our 2014 populations may perform very differently, if you will. So if we are to plan management programs based on the 2014 population and then apply it to the 2018, we may be surprised a little bit at the outcome. So what does all this tell us? It tells us that survival clearly varies with age and sex, and it tells us that despite all of the weird quirks of kangaroos, they still tend to follow kind of a similar pattern that we usually see in a lot of large herbivores, where primate survival is markedly resilient to variance in environmental conditions, or variation, forgive me. And senescent and juvenile survival is a lot lower and varies quite a bit from year to year. However, this variation was not explained by our environmental covariates, really. So nonetheless, these age differences have important implications for population dynamics, because they mean that population age structure could play an important role in the dynamics of this population. And they mean that essentially at the very least for females in the predator-free population like this one, survival from age about 1 to 9 is unlikely to be very sensitive to environmental conditions and to population density. So that's about it. I would like to thank everyone who made it possible for this long-term study to start in the first place, to keep it going even throughout a pandemic and everything, and to everyone who read and provided useful comments on my manuscript. I meant to add up there and I forgot, but this work has been published in Ecology as of December, if anyone is curious for more details. And I also forgot to put up my contact information up there. I meant to, so you're just gonna have to come say hi later. Thank you.
I see people can't wait to ask about it.
Hi, awesome talk, really fun. 2 questions. I think you might have talked about, and I'm forgetting, do you have a sense of what the population trends have been doing across time? It sounds like you have a pretty good data set for estimating.
Yeah, well, if you remember the curve we had for population density, it kind of had a very high peak around 2011, 2012, and then kind of dipped and has been more or less stable for the last 7 or 8 years. We do know their habitat is shrinking steadily, so which was accounted for in these studies, but is probably playing a role in that general trend that we're seeing.
Cool. And so were your survival estimates seeming to like align nicely with what trends you were observing in population?
Well, not necessarily, because if you remember, I mean, the senescent age class survival was kind of up and down all over the place. For juveniles, we had this kind of U pattern where it was very, very low in the middle and then high again at the end. And that doesn't necessarily follow the density curve we had, which is surprising. We have a bunch of hypotheses. We don't have any actual explanation for it. The objective for the last chapter of my PhD is to throw all of that information together into an IPM and see what comes out of it. So stay tuned.
Cool, good luck.
Another question at the top there.
Hi, very nice talk. Just out of curiosity, do you have any guess on why survival changes between sexes, like something about behavior or something like that?
Why survival changes between what, sorry?
Sexes.
Sexes.
Yeah.
Well, it's a pattern that we see a lot in a lot of large herbivores, and I couldn't tell you exactly why it happens in kangaroos, but a lot of the classic hypotheses have to do with either fighting. The males they fight more, they're more aggressive, just the cost of maintaining a bigger body size, perhaps. The kangaroo males can easily be 3 to 4 times heavier than females. So these are just 2 hypotheses that could apply in this case, but there are lots. There's riskier behavior, which also could be a thing. And in our population, males are also the bigger victims of roadkills, although it's still not a huge proportion. So anyway, lots of ideas, no definitive answer.
Thank you.
All right, we have to move on.
Thank you.
back to birds, this time with Morgan Miquel from the Swedish University of Agricultural Sciences, who's going to talk about age-related survival in the European crane population.
Yes, thank you for the introduction. So yeah, today I will show you a very preliminary result and also present you the project I started like 1 year ago. So it's about like European cranes and yeah, so the common crane is a large migrating bird that can be found across Europe, Asia, and also Africa. So this bird is migrating, so is breeding in the northern area over there in wetland habitats, and then is migrating during the winter in the south, where there is more abundant resources. So in this talk and also in the project, we focus on this part of the population in Europe and Northern Africa. So I will give you a rapid history of the population. So in the beginning of the 20th century, the population of a European crane was dramatic decline of its population until 1979, where the EU bird directive applied management measures to prevent hunting and disturbances, and the European crane was then classified as the highest protection. And then following that, at that point, around in the 80s, the population of European cranes was estimated around 14,000 individuals, and the IUCN was classifying it as a vulnerable species. But after that, in 1994, the classification of the European cranes was downgraded to near threatened, and from there the population knew rapid recovery. And now, in 2015, the European cranes is now classified as a least concern, and the population is now estimated as more than 500,000 individuals. So this can be viewed as a very successful conservation story, but this increase of the population is creating a lot of conflicts with human interests. So we have a first conflict with agricultural sector, because especially when they are migrating and in huge flock in the winters, are creating a lot of damage within the agricultural fields. But as they are also quite big birds and moving quite a lot and migrating, they are also creating conflict with because they can enter in collisions with aircraft or also power lines and wind turbines during their migration. So which creates conflict with those, different authorities. So that's why we decided to start the project to gain more knowledge on the survival and the demography of that species, and to therefore inform future management decisions. So for that project, I'm collaborating with 25 collaborators from 15 countries all over Europe. So this is my main collaborator. So most of the data is available in the ICORA database, or the internet-based crane observation ring archive, and also have observation from a lot of different projects. So in this project, we are using crane bending. So cranes are bended with plastic rings, so 3 on the left leg and 3 on the right leg. And this color combination allows us to identify the bird. So you can see here how the ring looks like when we are capturing and rigging them, and then how it looks like from afar. So cranes are typically bended as juvenile because then they cannot fly and then we can easily catch them. But sometimes they can be captured as adult when they are molting. So here is an overview of the data I managed to collect and assemble. So we can see here that here it's a distribution of the cranes that were bended. So most of the bended effort is in Germany, Finland, and Sweden. And in total in my database, I have now like 6,662 cranes. So in those 14 different countries. And now I will show you data on the reciting. So here we have also a huge observation effort from Germany, where the observation team and ringing team are putting a lot of effort. And then we can see then the distribution of the different observation. And in this data, I have more than 200,000 reciting in 42 different countries. So here you can see the number of bonded crane across years. So we can see that at the beginning of the project, of the bending program, there was like only a few individuals. And then now we have like all over Europe around 300 cranes bended every year. So in my data set, I have also individuals that were bended, so I said mostly as juvenile, but a few individuals that were bonded as adults. And it's really difficult to identify the sex of an individual as there is no sex dimorphism. So the only way to know it is if we observe like a breeding event or if we have data on the genetics. So on the result I will show you now, I'm only focused on the individuals that were bended as juveniles. So for that, I started by, as I said, only considering individuals that were bended as juvenile. I use the packaged R mark in R, and I just fitted like a Burnham model with both live and dead recoveries. So first I wanted to see if there was a difference in the survival and adult, juvenile and adult survival. And we can see here that even if it's not, doesn't appear, there is a lot of variability. Adults have a better survival probabilities than juveniles. And when we look at the variation across years, we can see that, both of the age classes have a high annual survival, but that in the recent years, so roughly after 2000, this survival probability is decreasing. So I also looked at sex difference in survival and also with age class, and overall males tend to have like a slightly higher survival probability, both for juveniles and adults. And as I said, like it was really like preliminary results. So I want to put more information into the model, like accounting for the birth country, And as some individuals were ringed also in wintering areas, so I have to kind of track down from which countries they were from based on the reciting, so they were recited in those areas. And also see if there is potential survival differences between the different migration routes. So in conclusion, as I showed you, the survival of juvenile is lower, and it's probably due to a higher early mortality or maybe first migration failure, and that we saw a decline of survival probability in recent years. So what I would like to do is also investigate the underlying causes of this decrease in survival, maybe by checking for density dependence, and if there is poaching or land use change or an effect of climate change. So I would like to thank all the collaborators from this project, starting by my close collaborators and the different coordinators from the different countries, as well as the ringers and observers from the different countries, and also the Carl Striggers Foundation for funding this project. And of course, thank you for your attention.
Right, question for Mona.
Do you know if misidentification is possible with these birds?
Yes, slightly yes. So there was a lot of issues in the dataset I received. So sometimes they couldn't know for sure which color was the band, especially like if the bird is quite old, like sometimes the colors can fade. So then if there wasn't like a certainty on the band colors, and I discarded this observation. And I also had the issue of color band code that were reused. And usually they reuse a color combination only if like the previous bird that carries that color died, but in some cases, different countries use the same color code. So I had to kind of find a way to differentiate between those individuals. So yeah, it's possible there is some misunderstanding.
So we had this evidence that if you have this decline in survival over years, it might well be that this is biased estimate due to misidentification. So
okay.
Have a look at this.
Yeah, thank you. I will look into that. Yes.
Did you look at potential heterogeneity of detection, resightings, or?
Not yet, but that's the next step. I would look into that.
Because just perhaps a word of caution, given the wide range of resightings, there might be, and very often when it's not taken into account, it may give the feeling of a decrease in survival. Okay. So you would probably get a better view of the survival decrease, accounting for recapture heterogeneity.
Yeah, that was what I wanted to do later on. Thank you a lot.
We have time for one more quick one.
If I understand it right, you're modeling apparent survival, at least partially apparent survival, not just actual survival. So some of that be immigration instead of mortality, causing that?
We don't really know. Like usually, in this analysis, I treated like the whole European area as only the same area. But I would like to look more in detail if like some cranes are observed in different areas, at the areas that were like banded originally, and but usually those birds have very high site fidelity. So if they survive, they will tend to return to their breeding, like the areas they were born in. So there is kind of like few, not really a lot of case of immigration.
All right, thank you very much.
Thank you.
Then we have Emilienne. I don't have
No, it's okay. Gregorzik.
We have Emilienne, who has the honor of having the last talk of today, and she's from the Office Français de la Biodiversité, and she will talk to us about whether hidden demographic heterogeneity is common or not.
Thank you. Okay, so I will talk about hidden demographic heterogeneity. First, I would like to thank all the collaborators I have on this subject. Okay, so what is heterogeneity? I'm sure all of you know some form of heterogeneity, like the difference between juvenile and adult, or female or male in most bird species. And this form of heterogeneity is easy to see and widely taken into account in population model dynamics today. But if we take an example of this population of bird with adult bird only and a female and a male, and we see more closely this population within this visible heterogeneity, it's remain hidden heterogeneity in each visible case. And hidden heterogeneity. Of course, this hidden heterogeneity is not like a mystical thing. It's can be due to many factors like migration strategy, cohort effect, personality, and but this kind of factor can be often not known or not easy to access. So sometimes they taken into models effect like this, but in most of cases it's complicated to have this kind of data. However, it's very important to take into account hidden heterogeneity. First, because it's influenced many demographic process, demographic parameter, demographic stochasticity, growth rate. So if we don't take into account this kind of heterogeneity, we can make bad estimation of this kind of parameters. And hidden heterogeneity and heterogeneity in general, it's an essential ground for selectivity and evolution. And it's even more important in harvested species because it's allows for compensation of all of or a part of harvest mortality. Indeed, if you look at this population and you consider that there is two groups of individuals, one high survival group and one low survival group, and if the harvest target mainly individuals of low survival group, then the annual survival rate will be less or not affected by the increase of harvest mortality in this part of this graph. And in bird, this study of Olivier Jimenez shows that there's many studies which are interested in hidden survival heterogeneity or survival heterogeneity in bird, but if we look at hunting species, you see duck, two duck, duck, again duck. So it's kind of, yeah, in this article. So maybe we can do better and make a more larger range of species. So during my PhD, I tried to understand if hidden heterogeneity is a common phenomenon in game bird species. And for that, I studied 6 species of bird, 3 duck, but 3 other species. And the species banding between 1963 and 2020. Only adults whose sex is no. And for the 2 species, the mallard and the teal, there is a historical and modern data set. Historical data set from this date to 1990, and modern starts in 1970. And for some species, individuals were occupied with saddle-nasm. It's allow visual, you can see the bird without have to recapture the bird. And for the kale, the trap technique just allow to capture male. So there is only male for this species. So in a homogeneous model, the probability for an individual to survive from the time t to the time t+1 is phi. And in our model, we have a population with 2 groups of survival, and an individual here have a probability phi to be ascending to the height survival group, and after that he have a phi probability to survive from time t to time t+1. On the contrary, if this individual is belonging to low survival group, he had 1 minus phi, the probability to belonging to the low survival group, and alpha, so survival differential, multiplied by phi, probability to survive from time t to time t+1. So these are the demographic parameters, but of course we have also detection parameters. So the probability of physical recapture, P, V, the probability of visual detection only for species with sudden nasal, and D, the probability of finding dead individuals. And of course, because we study hidden heterogeneity, we take into account the sex on all the probability, and only for detection parameter, we take into account the probability, we allow the probability to vary across time. So the departure model is this one. And we do a model selection by following the step-down method developed by Jean-Dominique Le Breton, and you can see this method in this paper. So we start from the detection parameter, and for each parameter we try many effects, and we select the best model via the ACC criterion, and we do that for D, and after for V, the probability of visual detection, the same for the probability of physical recapture, the probability of the assignment to high survival group, and at the end, we take into account both the survival of the high survival group and the survival differential. And in this example, for this model is the best model. So the result, I show you the detailed result for these 2 species. So let's start with the common kale. So in this species, there is a huge difference between the low survival group and the high survival group. And most of the birds were assigned to the low survival group because the probability of assignment to the high survival group is very low. But for the common SNP, there is no heterogeneity for the female, but only heterogeneity in male. For all the other species, so there is heterogeneity in most of study species, except the blackbird. And it was interesting to see that for the common teal, there is only, for the modern period, there is only heterogeneity for individuals with nasal saddle. So, like I say in the introduction, heterogeneity can allow for compensation in harvest species, but for that, hunters have to target individuals from low survival growth, and for that, we have to know what is created this kind of heterogeneity. So, we try to make a few analyses to understand why there is heterogeneity in this kind of species. So we try to understand the relation between the probability of being assigned to the high survival group and the body mass at bonding and the day of bonding. But sadly, we see no relationship between this variable and this probability. So the home message is that the presence of heterogeneity was very impressive in these 6 species, because 5 of the 6 species present hidden heterogeneity. So it can be a very common phenomenon in hunting species. But we are in science, so there is most of question after. So we want to understand after what other factor can explain the belonging to the high survival group, and how we can predict the degree of heterogeneity in species, because this kind of model necessitates many data. So for some species, it's not possible to have as many data as we have. And the last question is about the heritability of heterogeneity in these species. So thank you for your attention, and this work is just a part of my PhD that I'm finished in February, so I'm looking for a postdoc position. So if we want to discuss, I'm open to that, and again, thank you at all.
All right, time for about 2 questions for the end. Oh, there we go.
Nice talk. Any thoughts about why the difference between the nasal mark teal and the band only teal?
On the common teal with the saddle, okay. We see that the bird with saddle nasal have a low survival, and the bird without this kind of mark have a high survival. So first, and we don't really know, but maybe for some bird in this group, they are not support this kind of tag, and we don't really know why in this group there are birds that are really hard survival from the others. So we don't really know that. So no, I don't really have an idea for explain that inside this group, birds are not have not the same survival.
From the dead recovery part of the model, is there a difference in reporting rates between the 2 mixtures that might reflect different exposure to harvest?
At the beginning, we have a different probability between the 2 groups of survival, but we have many problems because it interferes with the probability to be assigned in the group of survival. So at the end, in this model, there are 1 probability of being dead, and we not separate the high and low survival group. But in the first model, we don't see this kind of thing. So no, I think it's there are not different probability. because the hunter can't see if the bird is a low or high survival group. So we don't really think that, for example, they report more the high survival birds than the low survival bird. And because it's hunting species, most of the dead recovery is from hunting. So no, we don't have this kind of thing.
All right. I think that then marks the end of the session. So let's have another applause for all of us.
Before we leave the room, I have two announcements. We have some extra room in the receipt for the excursion tomorrow. So if you did not pick up an excursion for tomorrow, you can choose one. And the second announcement is that now we'll have a poster session in the hall, and we'll have a typical French break, which is not coffee. You will see. Ouais,